different ages that you're teaching. So kind of diverse, and along with the grad students, we all come from different fields. So the goal of this experiment is hopefully, no matter where you're coming from or what your previous understanding is, you can find ways to connect and maybe as a group understand through the different models we present these cool phenomena that we actually see similar things to in our everyday life. So we try to start with the demo because it's stuff that's maybe a little more accessible. It's stuff that you maybe experienced before and didn't really think about it as a scientific phenomenon. But there's stuff here that connects to nanoscience, which I think when people first think of nanoscience, it sounds very daunting, very high tech. But we'll see that there's actually a lot of examples of nanoscience that we use in everyday life. It's in nature. So I'll start with that, kind of the premise. What is nano? It's basically the study of stuff that's really, really small. So this is sort of, a scale bar on its own, just comparing something macroscopic like a tennis ball to the idea of something really, really small, like a single water molecule. So when we talk about nano, sorry, I don't have a laser pointer, so I'll be using a mouse here. We're looking at this range here. So something that's maybe on the order of a molecule, like glucose. So not just one atom, that's 10 to the minus 10, a group of atoms. Or smaller things like viruses can also be nanoscale. Once you get into cells, that's a little bit bigger, usually like a micro-sized object. But the idea is that this is very, very, very small. So one thing that I've heard before, which is a little hard to wrap your head around, is that the difference between like a house and a strand of hair is the same difference in scale from that strand of hair to something that's nano. And if that sounds ridiculous, it's because it is. Nano is very, very small. So we have these things in nature that are nanoscale, like I mentioned, viruses. But as our technology has, rapidly expanded, we've also gained the ability to make and observe things nanoscale. You can see here, there's actually some like transistor devices that are, not quite nanoscale, but getting down there, and then, nanoscale particles, which is what we're going to be looking at today. So very, very small objects. And so when we want to interact with these things, like I mentioned, this is a billionth of a meter. You can't just see them or interact with them in a typical way where you tangibly touch it or, feel it. You usually have to investigate it through some other means of probing it. So for instance, if we want to image these things, because they're so small, we use electrons. And so one of the things that we have in CNSI in the basement here is a lot of different electron microscopes for studying these things. And basically the way that that would work is that you would direct a beam of electrons and then maybe look at how fast the electrons were coming back at you, or some other method of kind of indirectly measuring that surface through probing it with some other type of force. So this will be a theme that we come back to as well when we talk about color and light and how it's interacting with our nano objects. So this is actually some pictures that the original designer of this lab, which I will continue to shout out, Leonardo Scarabelli. He was a postdoc in my lab a few years ago. In his PhD, one of the things that he did was work on nanoscale synthesis to make all these different shapes. So we'll talk a lot more about shape later, but just kind of showing different ways of measuring these. We actually can get down to really, really small scales by using electrons and seeing, what are they bouncing off of, what are they not, are they passing right through? That's how you get these kind of high contrast images. And technology has gotten so good at this point that you can really take this to the extreme. So in this image here, you're actually looking at a particle, and these little dots here are the individual atoms. So yeah, that's pretty wild. And the thing here to really drive home is that when we talk about these nano objects or nanoparticles, the number of atoms that make them up is something very countable. So when we think of, moles or things that we interact with physically, it's usually a number that's so big, 10 to the 1/23 or something, whereas you could probably actually count how many atoms are in this particle. So because of that, nanoscale things have some interesting properties that typically bigger objects don't have. And one of the reasons for that has to do with the higher surface area that a nanoparticle will have relative to its volume. So a way to think about that, we have this example here. Let's say we have just this cube, you know, some 5 by 5 cube. If we were to take this same volume, but now slice it up into rows of 5 by 5, the volume of it has stayed the same, but suddenly the amount of it that is surface has increased quite a bit. So another way, my computer is, where's my mouse? Sorry, I've lost my mouse. So then looking at this, kind of connecting back to the particle idea, if we have something that is really small, and you look at how many atoms there are making it up, you can actually see that the number of atoms relative to how many are in the interior is actually, you know, pretty high. So this 30 to 22 in this kind of flat 2D example, those numbers are by all means and purposes pretty much the same, which is a property that you just don't get with bigger objects because so much more of it is inside in the inner volume. So when we have things that are mostly surface, one of the consequences of that is that they tend to want to react with things more because they're exposed to other things that aren't them. And we'll talk a little bit about that as it relates to something we have to do in our synthesis. So another property that nano-sized objects can have that is unique to them is that they can have some really interesting interactions with light. And that is going to be one of the focuses of today. So as an example, on the left here, we have, you know, a bar of bulk silver. We refer to things as the bulk when it's not like a nano-sized object. And it has the color that we actually just call silver. But below, you can see these two vials of liquid. These are actually vials of silver nanoparticles in a solution. And they're definitely not the color silver. You know, they're yellow, kind of this amberish red. And we'll talk about why that is. Another thing that can happen with nano-sized objects, if they're a different material, maybe a semiconductor, is you can get these sort of interesting fluorescences based on their energy transitions. So maybe you guys have heard of like QLED, computer screens and TVs that are starting to become popular. This has to do with nano-sized particles that have these transition energies, and we'll actually be hearing from a professor later who does research in not noble metal particles that we'll be making today, but you'll hear a lot more about this type of energy transition later. So one thing that I found was kind of interesting when I started learning about this is that the idea of nanoparticles giving these colors is not something that is necessarily new. It's more new to our understanding, but people have actually been using this in art for quite a long time. Examples in these stained glass windows, the Lycurgus cup, I'm never sure if I'm pronouncing that correctly, is actually from the 4th century. And this actually involves suspended gold nanoparticles inside the glass that was melted at the same time as the glass. And they didn't really understand that they were making, you know, gold nanoparticles, but it was kind of a method to like melt this mixture together, and they got these amazing colors. But this is one of the reasons that despite their age, these stained glass windows tend to not fade. So when you think of things like dyes or organic molecules or like plastic toys you leave out in the sun, over time they lose their color. Despite these being in direct sunlight, they still have these strong colors, and it's because the thing that's giving them the color is different from like a dye molecule that a lot of times we think of as being colored. So, moving on to how we're going to understand, before we start making our particles and experiencing this for ourselves, we're going to have to talk a little bit about what light is and thinking of it as a wave So the general idea, I've been talking about nanoscale a lot. Another thing that happens to be nanoscale is the visible light spectrum. So when we think of the wavelength of light, the wavelength of light that corresponds to the colors that we see is on the same order of nano. So typically when we think of visible light spectrum, we think of 400 to 700, 400 being kind of, you know, close to UV, it's more like these purple blues, and then 700 being red. So interestingly enough, it's basically the same size as the particles we're talking about. So the other thing that we have to talk about is we're going to be using metal today. So one of the things that I talked with Jeanette about was that a lot of times in at least my chemistry education, it's easy to focus on elements like you know, carbon, hydrogen, but this is actually talking about a different kind of set of elements that usually don't get a lot of love. And it's because sometimes they're a little bit more complicated to understand because they have more electrons. So one of the consequences of this, something like gold, is that when you have gold interacting with itself, there's electrons that are not tightly bound in direct covalent bonds, and they're sort of these exterior conduction electrons. And a way of thinking about this, people refer to it as a sea of electrons. So the picture that I want you guys to have is that when you have these metal nanoparticles, there's electrons that are kind of delocalized. They're able to move between the atoms. And so what happens, and this is sort of getting to the keyword of today, what is a plasmon? When we have this light that is the same order of wavelength as the particle itself, interacting with this particle that has this kind of sea of electrons, what can happen is that these electrons can all be oscillated by the electromagnetic wave in phase with themselves. So they're all collectively moving together to one side of the particle and then to the other. And so this is called the plasmon resonance. The frequency at which this happens, or the wavelength that is corresponding to that, is the plasmon resonance frequency. And that is going to have to do with the size of the particle, which we will talk about. Another way to really think about this, so I have this little clip art here of a swing, is you can imagine if you're pushing someone on a swing. There's a certain frequency that you are going to be pushing in order to time it right so that you're giving them this boost. If you do it too fast, you know, it's going to get all jumbled up and they're actually not going to be, you know, swinging very effectively. There's going to be some speed based on, you know, how long the swing is that you have to push. And that's the same idea as there's some frequency that is particular to this particle based on the size that is going to allow these things to move from one side to the other. So how does this actually give things color? Well, when things are in resonance and this phenomena is occurring, whatever that frequency or wavelength, conversely, is, whatever that frequency is that is causing this resonance is actually going to be absorbed by the particle. And so another way of not looking at kind of the spectrum linearly, but more of like an artistic style color wheel, if something is absorbed, we tend to see the thing that is not being absorbed. So kind of checking in with you guys, if we're seeing something that looks green, what color is being absorbed? Any guesses? Excellent, I heard it, red. So that's correct. No dumb questions. That's a great question. So later on in the talk, I'll kind of mention what we kind of use, or what we find as applications to these things. But one of the things that happens to these particles is they can get very hot. So yeah. Yes? That's a good question. So the thing about the chunk of metal is that it's so much bigger than the wavelengths of light, and the size of it is so big that it's not going to be possible to achieve all of the electrons in the whole material moving to one side and then the other. So I'll kind of go back to this picture here. One of the reasons that as I mentioned, like these get very hot is because it sort of intensifies itself, like the swing. If you're able to get every electron in a particle to move to one side, suddenly you have all these negative charges on one side and a net positive on the other side. And then you can imagine, well, now the electrons want to go to the positive side. And if that is happening in time with this electromagnetic wave, it becomes a very intense phenomenon because it's driving itself, and that is what we call resonance. Yes. Yes, it's a little bit of a different model, and another thing we'll talk about towards the end is when you start to see, so we're just talking about like absorbance right now, but there's some other things that we can bring into the picture, such as scattering, but we'll save that for our part 3 of the experiment, and hopefully we'll build off of that. But thank you, Dima. Yeah, so this is sort of our reasoning why when we see some of these colored nanoparticle solutions, it's because they're absorbing this frequency. And a good thing that was pointed out is that the energy doesn't just go nowhere. These things actually get quite hot. All right, so we're almost ready to start our experiment. Instructors, get ready. So what we're going to be doing as our first experiment is actually synthesizing some gold nanoparticles. And we've developed a protocol, well, someone developed a protocol a number of years ago that we've adapted. That's actually quite straightforward, but it requires a few things. So we need to be able to generate atoms of gold as opposed to ions. So we're starting with ions because that's what we're able to like buy as a solution. Specifically, we have a gold salt. We need some way of turning these from charged particles into neutral particles, so that's going to be part of it. And then we need these atoms, sorry, not particles, we need these atoms to come together and then form the particles, and then over time grow to some size. So more specifically, we have our gold salt, which is going to be a source of gold 3 ions. So when we buy it, it is this gold chloride. We then have a reducing agent. So this is turning it from a +3 into just gold itself. And so this has all the electrons. You know how I mentioned there's going to be this sea of electrons? We can't have them be these electron deficient gold salts. And then we also have a capping molecule. So once we form these particles, what really stops them from growing into gold? Like, why don't we just make a gold sheet or something that is the color we imagine? And it's because we have something that is going to keep these particles from running into each other. And this also kind of ties into the idea that when you have nano-sized things and there's so much surface, they have a tendency to want to react with other things and keep growing. And so part of our protocol is going to also have a molecule that is going to repel them from one another. In this case, the convenient thing is that the reducing agent and the capping agent are the same thing. So, makes it simple. All right, so at this point, you should have a manual. I don't have the same one. I believe so I don't know exactly what page it is, maybe page 9 or 10, but under experiment 1, it's going to have some direction. So what I would like is for you guys to break up into groups of 2. You guys can work as a group of 3 or 3 group individuals. It's kind of up to you guys. And then one person from each group will come up and collect a set of reagents from a grad student. You guys have one hot plate. You will have to share it. So be mindful if you're at the part where you're heating up your solution that everyone knows that it's hot. And yeah. Do you just want to pass them out? 'Cause that's all right. Forget about coming up to the table. We'll be passing them out to you.
find a table and kind of hover around them and make sure that people don't have questions or, I mean, the instructions should be designed that you can follow them.
Are they going to do all the experiments now?
No, they're just doing part one.
Okay, because they were
So essentially, like this first part,
Hello, people on the internet. So I'm gonna ask. So do you guys mind? So we have the camera focused on this table just to like see what's going on. No, please play. Please stay. No, well, I mean, yes, that too. But also, do you mind if we place the mic here so
Yeah, of
that we
course.
can hear the conversations that are happening?
Yeah, sounds good.
Okay, awesome. Thank you.
For the stars of the show. Wait until we make our gold nano stars. It's really gonna be appropriate. Yeah. Yeah, so you can see there's bubbles starting to form at the bottom. So it's not quite at a boil yet, but it's getting there, right? And so remember from our instructions that once it's like actually boiling, we want it to stir as fast as it can go. That way, whenever we put in our capping agent, our incubator, everything happens all at the same time. And if you're stirring really slow, then right where you inject it, that's going to start growing first, and then it's going to have to diffuse. Yeah, so if you flip to the next page. Oh, it is hot, yeah. Once you inject the solution B, we're going to start growing nanoparticles, right? And as we talked about earlier, once the nanoparticles are on the scale of the wavelength of light is whenever they're going to start giving us a visible target. So right when they start doing this, well, the ions are already in solution. It's a salt. So it comes as a powder, right? It's a solid. It's like sodium chloride. Quickly, and if you go quickly, it should be all the same size.
So
Okay.
this promotes reactivity.
Yes,
Once
yeah,
we
yeah.
introduce solution.
Yep. So now we're at a good boil, so we want to stir it as fast as it'll go.
Let me get this ready.
Nice. Yeah,
You want us to move it to center?
if you could, yeah.
That's
Just
it might be hot.
touch it briefly. Yeah, that's better. That way it's vortexing, you know.
Almost quite there.
There it
There
is.
you go. Oh, text me back.
So now we get a little whirlpool. Okay, so now you're ready for solution B. So it is 0.5 mils. Oh yeah. Actually,
Oh, where's the
I think you have like a big air bubble here.
Yeah.
Yeah. So the easiest way to do it is to pull it like all the way up
Okay.
and then push down until you get to the 0.5. That way you can see where the line of the solution is. Yeah, so right there. Right. It's the same thing with the meniscus, like on a graduated cylinder. You just
And then I start my clock as soon as she adds it.
yeah, and so you want to add it as fast as possible
okay.
because we want everything to start growing
Do you want
at
to
the
come
same time.
Sure. All right, we're doing this. Ready?
Yes.
Yeah.
Timer.
Got it.
All right.
The color.
So remember, once we start growing, we're at single atoms, right? We start at single atoms. The single atoms are coming together, but we're still too small for the plasmon resonance. So over time, as they start to grow and get larger and larger, they'll start to interact with visible light, right? Right now, if it was interacting with wavelengths, it would be ultraviolet,
Yes.
right?
Yeah.
It's too small to see.
Yes. Ah, I'm
Oh,
starting
I
to see
see.
a color change.
Yeah.
Yeah. Yep.
But it's time until color stops changing.
Yeah.
So
Yeah.
we have to just wait.
Darker and darker.
It's a tough one to see when it stops changing.
Yeah, you'll. It's actually a very gorgeous color
Yeah,
at the very
you'll
end.
see.
Get it right there. Like a nice lavender getting to it. Oh, it's pink now? Wait a minute.
The kids will love the color change.
Yeah.
Like a magenta. I don't know.
It's like grape flavor.
Yeah.
Great.
Purple
Right, so
drink.
this
Yeah, exactly.
Yeah. So now our nanoparticles are large enough to be interacting with light, doing the plasmon thing, right?
I see. I see. Interesting.
And as they grow, the frequencies that they're interacting with are changing, which is why we're getting different colors.
Oh, it's like a little reddish, huh? Yeah.
Ruby red.
Yeah, red.
Yeah. So you should end with kind of like a ruby color, and
Almost there.
the reason it doesn't grow more than that is because we only have a certain amount of gold in the solution, right?
Purple. Red. Orange next?
I think this is about the last color that we saw, so we'll see. We'll see if it gets any change from here. But whenever we did this experiment, it ended about this ruby color.
So should we mark time?
Yeah, I'd say about.
2:20.
Yeah.
2:30.
And you can just watch it for another 30 seconds and see if it changes anymore.
Okay.
I suppose it's up to how you want to do it, right? To just say that we noticed the colors changing.
Yeah, so it looks like you're done. So
Okay.
now we're on step number 9.
Reduce the strength. Mid-level. hot
Me and
plate off.
Katie didn't do. Actually no, we did do this exact one because we did try it with citrate. But then
Yeah,
we
so there's not really a good
changed
way for us to take this off the hot plate and let it cool a
Right.
little faster because we will melt the tablecloth.
Yeah.
Put it on here.
You
Might-
could, but I think it's okay. The best way that we found to get it off the hot plate was to use like a paper towel oven mitt. You know, kind of grab it, but that might be a little dangerous, so we can just leave it.
Yeah.
Probably
Um,
with students, you want.
Well, on that
Or use
table,
tongs.
they basically grabbed it with a napkin and just immersed it in the water a bit. But yeah, I don't know if I would trust high school students to do that.
Yeah.
Yeah. Maybe
Okay, so
tongs.
it looks like we had a successful batch that we just made.
Yeah.
If you guys want to try and repeat it,
Okay.
Yep. Let's do it. Oh.
Your turn.
Oh, okay.
Yeah. Also, remind me, what do you guys teach again?
I'm elementary science.
Okay, cool.
Katie.
You're the course.
Katie was a
Yeah.
teacher.
Oh, really?
Yeah, I taught middle school science like last year.
Where?
And then, it was in Arizona, so
Okay.
it was at a charter school.
Yeah, I taught middle school science too.
Really?
Yeah.
It was,
And
it
the
was-
middle schoolers were just so kind.
I know. I really enjoyed it. They're like super excited about everything too.
I was being sarcastic. Oh, they drove me crazy.
Me too.
I love elementary. Yeah, they're so sweet.
They were curious, but also evil.
All right, so we can get our.
So let's put some, maybe like a layer of napkins. Pull it off. top of.
Yeah, you want me to grab it off?
Yeah, right there, and then maybe.
Are we putting it in the water,
Have like
or
another napkin.
Just kind of cooling it down, I think, like this, right?
Yeah.
Are you okay?
Oh, looks good.
Alright.
Here.
Yep, sweet.
Yeah, and then you can leave it on the paper towels and it'll cool off.
okay?
All right, so we can get our other solution
Part
made.
two? So here, I'll label it.
Can we use the same one, or do we use? A
Yeah,
different
you
set?
can use, or, I mean, I guess it doesn't matter.
Yeah, you can use the same.
Yeah, just so we don't have to dirty
Here's your
plastic.
first solution.
Sweet.
Miriam, you okay taking time again? Or you want me to take time?
I think I can do it. Tough job,
The official
but-
timekeeper. Yeah, so now that we don't have anything on the hot plate, we can turn the stirring off.
Oh, yes, thank you.
Yeah, so the things that affect the eventual size that it grows to mainly is the amount of gold that we put in, right? So we have a controlled concentration of the solution A. So there's only enough gold available to grow to a certain size. And then the capping agent keeps it from growing beyond that. So we want to prevent each of the nanoparticles from coming together and making something bigger. So the capping agents are going to, keep everything segregated.
The capping agent, as long as it's enough, it's not going to affect the final size.
Right. Only the
Only the, not mostly the amount of gold.
yeah.
Some more solution B in there. Should
Not
be
as
right.
much. So you might want to.
That's enough.
Is it enough?
Yeah, I can squeeze that in there. 0.5.
But we
Yeah,
don't
so
add that yet.
we have a certain
just gonna get my
concentration
prep
of the
ready.
A
I
solution,
do a time-lapse video of this.
and then we give
because I love
them
watching the color change. Hot plate on.
tell them, okay, 25 mils of that, right? So if we gave them less, they would grow to a smaller size. So if we said, okay, only put in 10 mils of the gold solution, right? It would become smaller.
I'm just thinking because it's evaporates.
Yeah.
More and more concentrated.
Yeah, so this is getting more concentrated, but if our capping agents are doing their job, they shouldn't continue to grow after the boiling point, or after the reaction that gets it to the.
Inject solution B.
The temperature just helps with
Just wait for it to boil.
Yep.
Yeah, it helps our. If we grow faster, we should end with a more uniform size distribution.
I'm gonna try like placing it.
you know the average diameter of the gold.
I think it's 100. I think it's 100 nanometers. I could be wrong.
We're passing around the vials for section 2 right now. So the ones that get labeled 1, 2, and 3, you don't have them at your table yet.
Can I see your syringe?
Yes.
It can be a little tricky sometimes if we get an air bubble. Yeah, so see you have this really big air bubble right here?
Oh, I didn't even see that one.
Yeah, so the best way to do this, can you open? The best way to do it is to just go like all the way up.
Go past it, right?
Yeah, and then actually something also that helps is if you draw a little bit of air into it, you flip it over,
3 vials.
tap that bubble up to the top. So you see we have our air bubbles up at the top now. And then you can push these out. There we line it up to the 0.5. We had
We have the vial.
But do 2 sets.
okay.
Oh,
Two syringes over here.
And so we were just talking about what controls the ultimate size that these grow to, right? And you could think of a few different factors, right? Like how long it goes for, right? Because as it was changing color, if we maybe took it off of the hot plate, right, would it stay that size, or would it want to keep growing? Or maybe if we didn't have the hot plate boiling, right? If it was just like a little warm, or maybe if it was cold, right? Those could also change what size we get in the end. We should do SEM on these.
Yeah.
I mean, it's only a couple rooms over.
Yeah.
Let's go put it on the Titan. That thing scares me.
The Titan.
Yeah.
I know, me too.
I'm glad I don't use it.
I know, I'm like, don't breathe on it. My brain.
They were just like
Yeah, we have a giant electron microscope in this building. It's like 10 feet tall. It's millions of dollars. It's kind of intimidating.
Yeah.
I just saw it when I visited. Like they just show you all the facilities, and I was like,
Yeah.
That's awesome, man.
Yeah.
That's what I did my grad work on.
Oh, really?
Bio-EM.
Yeah,
That's
yeah.
what I worked on, yeah.
nice.
Yes, I remember.
Yeah, any machine that's many times my net worth, I'm like, don't let me touch it.
Try to not break anything.
Let someone else do the dirty work.
Right?
Like, yeah, it was their fault.
And so you can see, you can see this flask of nanoparticles that we made. It's been sitting for many minutes, right? It only took 2 minutes for it to grow, but it's been, maybe 5 or 10 minutes since then, and it's still the same color, right? So that means if it's the same color, it should be still the same size, right? So it hasn't grown anymore since we took it off the hot plate. So that means the capping agents are doing their job, right?
Are we boiling?
Yep. So get it
add
stirring,
solution A?
get it stirring nice and quick. Yeah, I would say that's ready to add.
Stir up higher?
Yeah. And whenever you inject the bee, try and just don't get it on the walls of the flask. Sure. Right? Try and go straight in.
Okay. You ready?
I'm ready.
Nice. And so immediately the color, it's no longer that straw color, right? As soon as we put in the reducing agent, we don't have that same color anymore because the gold isn't in the same state. It's gone from +3 to 0. Everybody is getting in on this.
Like a TikTok.
Oh, that's too advanced for me.
A kid. TikTok science.
This would be a good one for it.
It would be actually.
Very visual.
So pretty.
Yeah, I know. It
Changing
looks,
again.
I think it's gonna stop right. Yep. Okay,
Now it's that ruby red. Wow, it's so pretty.
Yeah.
Yep, that looks about the same as the other flask. So again, about 2 minutes, and then you can let it go a little longer and make sure it's not going to do anything else. But you can tell, right, that when it starts small, it looks violet, and as it gets bigger, it goes across the spectrum to look red.
That makes sense now.
Yeah.
Okay.
So you think it's gonna stop?
I think so, because we put the same amount of gold in,
Yeah.
right? So it should end up at the same size.
So if we use more, would that?
Yeah, so say if you put in, you know, instead of 25 mils of gold, of that gold solution, if you put in 50 mils of that gold solution and put in the same amount of the capping agent, right, you would expect that all of the gold, you know, right now it looks like all the gold is reactive, right? Everything's made a nanoparticle and then the capping agents are surrounding it. But if we gave it extra gold, it would be able to keep growing, right? And the capping agents are keeping the particles that we've already formed from seeing each other and getting bigger, right? So that's why this still looks the same even after all this time.
Awesome.
So
That's like
would we
perfect
expect to see
stuff.
a different
Very
color?
I like
Yeah, yeah, because the size
observations in
depends,
the back.
the size determines the color that we see. And so if we put in less gold, right, if we only put in 10 mils instead of 25, maybe it would be that purple color that we saw earlier, and it would stay there.
That would be an interesting guided experiment. For this.
Yeah.
Yeah.
See if you can control the
Here,
size
I'll
by that.
post it. I'm gonna post it on
So
my.
now we are
my
done with this, so we can turn the hot plate off, turn the stirring off, and get it on our little cooling tray.
Yeah, then you just do it and then
Make it a
it's
story.
yeah. It's good for like sunset.
Yeah, so let's get it on the little napkin, and then we can move on to the second step.
That could also contribute, you know, if you, again, like let's say you have a scatter and, you know, you're sending in the light and it's
Good.
the thing is that this scatter can interact with another particle, right? The visibility of this happening is higher.
Nice.
So you can have them close by and they can see each other. And the thing is,
I'm about to be making
So we probably want this one to be more like room temperature before we go on. So maybe we can dunk this in the water. This earlier one.
It's okay. Like,
Yeah, it's not that hot anymore. Yeah, so now in section 2, we want to be careful about what glassware or plasticware we're using, because we don't want to introduce more gold solution if we use the same cylinder that we measured the gold with, right?
All right.
So that's why it says, you know, use the graduated cylinder labeled nanoparticles, so that we're not
okay.
introducing more
I
of
see.
our growth solution.
That makes sense.
Question then.
And so that is actually really important, because as we were just talking about, right? If we put in more gold, what's it going to do?
It's going to change the color.
Yeah, it's going to get bigger.
And we want the nano.
Yeah, we want it to stay about this size.
A little bit more.
But I mean, I get what you guys mean about the whole contamination, but wouldn't this need to be heated in order to start growing particles?
Well, not necessarily. So the reason that we heat it up is so the reaction's fast, not necessarily to let it happen in the first place, right?
Got it.
So you can grow nanoparticles colder, but it's going to
Takes
be more
longer.
distributed because there's less energy in the system.
It's, I mean, what's kind of like bugging me is at what point does it start growing?
Yeah, right. Like at what temperature?
Yeah.
Like if you had like 1 degree C water, would it still grow?
I mean,
right?
isn't it already growing when you guys bring it to us in the solution?
No, because remember, this is a salt, right?
Yes.
So this is a gold-free chloride,
Yeah.
and all of the gold atoms are positively charged, so they don't want to come together. The stuff that we're putting into the solution is a citrate, which reduces the gold, so it goes from positively charged +3 to 0. And when it's neutral, that's when everything can start to add onto each other. Right? Because, you know, if you have a bar of gold, the oxidation state of the gold in the bar is 0. Right? It's metallic. So nothing can grow until it gets into that metallic oxidation state.
Okay, that's good.
All right, so let's go on to section 2.
It's gonna be page 9.
Measure about 5 mils of nanoparticles using graduated cylinder label nanoparticles.
Sure. Where are we at? I lost
Page 9. Base
they're
plastic?
yeah, they're plastic.
Is that going to be an issue?
What?
No, it's
No,
just
no, no.
these usually come as glass.
Oh, I see.
So we use the new
Yeah,
ones?
yeah. Well,
Yeah.
you're gonna use. Oh yeah, for the syringes. Yeah. So on step 3, yeah.
For step one.
For step one?
We'll have a graduated cylinder.
Okay.
Yeah. Because we want to measure out 5 mils, and those only go to 1, so you
Got
go
it,
from
got it.
1, 2.
And then does it matter
And
which
then
one we
this
start
one's
with?
the cool.
Yeah, we want to use the one that's the most room temperature.
Actually have this app that looks at breakdown of red, green, and blue pixels.
Okay.
Okay, so that's our vial 1.
Label this.
So you can
Vial one, yeah.
so you can put that yeah.
72, but it has the pixel numbers are
And if we have a vial 1, you can guess what the next one's going to be. Okay.
Okay. Repeat this for another process scintillation vial. Label the vial two.
Also, if there's anything confusing in the directions, let us know.
Oh, that's fine. You're good.
That's okay?
Yeah. You don't need to get every last drop.
Okay.
So then same deal for vial 2. Just put in 5 more mils.
I can use the same one?
This is the cold one.
Yeah, just yeah.
So maybe scoot that one over.
I think it doesn't like the lights. It's freaking out. This is a free app we used for hours a minute ago.
The bottom particle still will adjust. The size will be more distributed.
Yeah, as long as you're above the activation energy, right? Which I don't know what it is for this system, but the idea is that if you're as hot as you can be, right, in this case of boiling point of water, there's so much energy in the system that everything can start growing at the same time. If you're colder, there still might be enough energy in the system where you have some portion that is able to start the reaction, but some portion that isn't. And so then you'll have some particles that grow bigger and some that grow smaller. So then you don't get a uniform size distribution.
There's no NaCl in there?
As long as we are over the activation energy,
Is there
it
NaCl in that
should
one?
not matter. I thought there is an optimal temperature.
Yeah, so you just want to be like, you just want to be hot,
We
right?
just want to be over that, so
Yeah,
it's better
yeah.
to be hot.
Yeah. I believe.
But I don't oh yeah.
Okay, so we got vial 1 and we got vial 2. All right, so
Air bubbles in this.
Just returning to the question of what's in the
yeah, so you can pull a little bit of air into it. Yeah, and give you some space and then tap it. Yeah. That looks all right.
I have it stuck. Should I just redo the whole thing?
Just give it like a whack.
There
There it is.
All right, nice. Little hacks.
I can't think about I have we like used to use silver nitrate in AP Chem and I remember
Did you get it on your
I
hands?
would get it on my hands.
Well, now since your syringe is fully filled with liquid, you shouldn't draw up any air,
Look like you're
right? So if you
Oh, I
just
see what you're saying. Yeah.
yeah.
I remember that. I don't even remember.
I should be able to do this.
But I remember.
Yeah, so you should be good at just 0.5. And so we were talking earlier that this stuff stays the same color because we have capping agents on all our nanoparticles, right?
And so like
And if we have capping agents on our nanoparticles, that means they can't continue to expand. Everything's
What is the capping agent?
so it's citrate. If you go back and look, we have a solution of sodium citrate.
Okay.
So sodium is going to be the positively charged thing. Citrate is going to be the negatively charged thing. Negative means it's going to add electrons to our stuff. So we start at gold 3+, and this adds electrons to our gold until it becomes gold 0, right? And so in addition to reducing the gold into gold zero, it also has a size and it wants to coordinate to the gold atoms. So the oxygen molecules, the oxygen atoms on the citrate, you can see they actually coordinate to the surface. So we have these little carboxylic acid groups that coordinate to the surface of the metal.
You then added in this, oh, thank you for that, Mike. In this case, this sodium citrate ions, and then you were creating your nanoparticles. So just kind of a quick test of your understanding and see if we have any guesses. If you round up with a ruby-colored solution, what color do you think those nanoparticles are absorbing? Any guesses? Green, yeah, awesome. So, and that's exactly what's going on. If you take a absorbance spectrum of these particles, you'll see that they have this peak in the 522 region, and that's exactly green light. So what we're then seeing is what's not being absorbed, which is going to be mostly the red wavelengths here. You can see very little is absorbed in like the 700. So awesome. The next part was to look at some of the stability effects based on two different things that you added. So can anyone tell me what happened when you added your sodium chloride to your solutions? They're black? Okay. Yeah, so they change color. What's with that? So what ends up happening, and one of the things that you might notice if you look at the supplies list, is that for this part, this sodium chloride was actually quite concentrated. I believe it was 1 molar? Something very, very salty. So what ends up happening in this case when we add the sodium chloride is that this influx of ions kind of disrupts what our capping agent was doing. So the capping agent, you can see these, here's my mouse, these citrate anions here. Basically how they function is that you have these kind of negatively charged oxygens on the citrate anions on the outside, and those negative charges are kind of repelling the other negative charges from the other citrate ions, keeping the gold nanoparticles from, crashing into each other. But when you throw in a ton of these sodium ions, suddenly you now have like positive charges, and those actually start to kind of bring all this stuff together, and you get what's called crashing out. So you can see here an example of what it looked like in your particles. And then if you look at the absorbance spectra, you can see pretty drastically, suddenly you just don't have these nice nanoparticles because they've kind of gotten bigger. Some of them start to, form clusters. And if you just let this sit for a while, you'll actually see it settle to the bottom and create kind of like a black gunk because it's just like a bunch of particles that are no longer these nice nano-sized objects. All right, so what about the soap? Does anyone want to take a stab at what they think happened with the soap?
So the soap has polar and nonpolar.
Right?
So you're surrounded by these negative shield. I don't know. Somebody help me?
I like the direction you're going in, where you're saying, okay, it has polar and nonpolar. It's something that it isn't going to have the same sort of interaction. It's definitely not going to be bringing these things together. So it maintains the size. So this is something that is not maybe obvious right away, but what actually happens, and you might have heard this term before, something that is a surfactant. So the soap, when you introduce it to your particle solution, essentially starts doing the exact same thing that the citrate anions were doing, and it starts to kind of coat the particles. And because you have these polar and nonpolar groups, it also does the same thing where these nonpolar groups, hydrocarbon chains, whatever the actual soap is, are also just repelling one another. And so when people are designing their particles for different applications, one of the things they think about is picking a surfactant molecule or one of these molecules that kind of fits the environment. In this case, we have our particles in water. What if you were trying to make them in something that wasn't water? That's something that I know Katie from our group has been working on quite a bit. And then what if you need your surfactant to be something, safe for biological molecules? These are all considerations.
Which directions are the stuff facing? The polar out or polar in?
Probably polar in, and then non-polar out to keep them, yeah. Because if it was polar out, then they would probably be interacting with the water. Does that sound right to everyone? That's a good question, though. Yes, it displaces the citrate because the citrate in this case is not actually like covalently bound to the gold. It's sort of just associated based on the size of the citrate ions and the fact that the electrons in those are polarizable, but it's not strongly bound to the surface, which is why in this case that capping agent is very easy to replace. Some of them are not so easy.
So then wouldn't you think that the gold itself would be non-polar, so you get the non-polar soap, and then the polar part of the soap would be out in the water?
That's an interesting idea. So the gold itself actually is fairly polarizable because of how many electrons you have that are free. So like that particle itself is polarizable, you could say.
Polarizable different than polar? I mean, I don't know. That must be interesting nano phenomenon.
That's a good question. I think when you think of polar, what I think of at least is thinking about one molecule, whereas like the particle itself is not necessarily permanently polar one way or the other, but it is polarizable because you can easily move the electrons back and forth. So it's not inherently always polar.
Polar is like water is polar because
yeah,
what you do is going to have the polarization.
Right.
Yeah.
The polarizable you can make it polar.
Okay. Yes, the sodium citrate was our reducing agent in this case. So that's kind of like the convenient part. When you first injected that really quickly, you probably noticed it pretty much started changing color almost immediately. Yeah, so there's a couple other things about that we can discuss that we will sort of revisit in this next part, where you notice that it went through a couple different colors before it finally landed on this ruby color. So for this next part, we're going to be investigating, we've talked about how the size is related to what that resonance frequency is, but how does shape influence that? So an example here, kind of just geometrically showing that, sorry, could you guys keep it down a little bit? Kind of showing that if you have something that is maybe spherical and uniform, you probably just have one frequency. But what happens when you start to change these axes? Suddenly what can happen is that there can be more than one frequency causing resonance across these different axes. And these actually can overlap and exist multiple frequencies that cause different resonances in the same particle. So an example here would be if you start to grow perhaps like a rod. You're going to have one frequency in this axis and then a different frequency that causes an oscillation in the z direction. And so kind of the idea of the spectra here, you maybe would have an absorbance in our green, but then maybe all of a sudden you're also absorbing in the red, and that's going to influence the final color that you see, because it's going to be all the things that aren't absorbed from there. So there's actually a whole field of research, and this is sort of what the postdoc who worked on this originally did in his PhD, was make these synthetic methods to grow these very uniform, consistent shapes. And you can see that there's a variety of colors. He sort of false colored the different images here. But yeah, the spheres typically red. These like rectangular cube thingies are green. And then triangles are very blue. So we're going to be growing a different shape here and seeing what color we observe.
Are those still gold?
They're all gold. So that's, yeah, a good question and good to remind yourself, because even though we have all these very different colors, the actual chemical identity is the same. It's just the shape and how the light is now interacting with it. Okay, so this can be kind of a challenging field, and the reason why, you know, people devote their entire PhDs to figuring this out. But one strategy that we can use to grow different shapes is to start with what we're going to call seeds, which are what you've already grown. We have very small spherical particles, and then through adding a variety of extra compounds, we're going to control the direction that when we add more gold, how is that joining it? So you're going to be collecting, or I think we'll be passing out solutions for this next part to each table. And so one thing that you might notice is instead of just having a reducing agent, we also have some other solutions, in this case a silver nitrate. So I will say this because I know that this is a question that is not the easiest to understand. Why are we adding silver if we're growing gold nanoparticles? So what the silver is actually doing in this case, when you mix it all together, is interacting with certain planes of the gold crystal and controlling where the next gold is going to come in. So this process is not something that you necessarily could do just by looking at it on paper. This is the result of a lot of trial and error to come up with this optimized synthesis for how these things grow. And essentially what you're going to be getting are spheres with different rods poking out of them at these different faces. Yeah, so we call them gold nanostars, but they're essentially spheres with little arms. But they kind of look like this when we grow them. And so that's what we call like a shape directing reagent. All right, so on to the next step. Grad students, I see that you're starting to pass out the solutions. Where'd Natalie go? Another thing that you guys can do is start clearing off stuff that they're not using anymore.
so before we do it, what do you think is going to happen?
It's like,
Right, it's stayed the stable ruby color the whole time because the size and the shape haven't changed at all.
I think it's just
I was here confused. Is it the line right below?
Yeah, so you can see this, go by the level of the solution, so just push it down to 0.4. So you have a little air bubble at the top, but it doesn't matter because you have the right amount of solution.
Okay. It goes into growth 2. What do we think's gonna happen?
oh yeah,
Okay, growth 2.
So it says growth, right? So what is going to happen to our gold nanoparticles?
It's gonna start growing.
Yeah. And if they grow, what happens to the color?
It's gonna change.
Yep.
It's gonna change. Change.
swirl.
Ooh, look at that. Like a light pink.
That's pretty. Kind of pearlescent.
Yeah, it is cool.
They will have to share solution.
So what is, to me, it may not be obvious if you haven't done this kind of work in a while, but it reminds me a little bit of like a colloidal solution like milk, right? Milk scatters light, which is why it's white. Right? And it's because it has little fat globules and proteins and stuff that are on the ordered wavelength of light. And so that's why it has that milky color. So this, to me, looks a little milky as well. And that can indicate to you that, you know, this stuff is absorbing light and retransmitting it, whereas this stuff might just be scattering. I mean, I might be getting ahead of myself, but that's what it reminds me of.
What is that solution?
And then,
This is our growth to
seeds.
Okay, that's the seeds. Okay.
Okay, so then the last step now we're going to be adding our ascorbic acid.
Yep. So rapidly,
add the contents of plastic
and
vial labeled ascorbic acid.
we're gonna get a timer ready.
I have my timer. Do you want to pour it and then I'll time it? Oh, we pour all of it?
Yeah.
I think so. Okay. Can you guys see?
Yeah.
1, 2, 3.
That was really fast, right?
Yeah.
And so shake it up, cap it and shake it around. So we've completely changed the color, right? Shake it a little harder. See if it changes anymore.
It's like a violet.
Yeah.
Not a violet. Indigo. Yeah. And that's it.
And so now it's stable, right?
And are we done? So pretty. So let's say 30 seconds. I was gonna say it's similar to this. I mean, it was less, but.
But that one has some particles on the bottom, right? Because it crushed out.
Check out the colors on this. Wow.
I think we're good. Yeah. Oh,
Do better distributing, baby.
Look at indigo, we said.
here they're doing it.
If you look at this sideways from the bottom up,
Ah.
see how it changes.
That's crazy. Yeah, you can. It almost looks like some stuff is like floating around in there, right?
Yeah, it's got some cracks.
So it's destabilized.
Yeah.
And what is that solution?
That's the one that has the salt in it. That
Yeah. And so if you want to think about it, you know, in chemistry terms, why would adding salt disrupt the capping agent?
Unless it's really strong.
Because it kind of takes it away.
Well, so our capping agent, let's go back and look. It's on one of these pages.
So the capping
Sure.
agent is
Stops the growth.
interacting with the electrons, right?
Iron is ferromagnet. It's the actual real magnet.
Yeah. So here we go. So we add some citrate to our solution, and the citrate is this negatively charged thing, right? And if we add in sodium chloride, what is in sodium chloride? Right? Whenever it goes in solution, yeah, it separates into positively charged sodium, negatively charged chlorine. And so our sodium can then find this citrate and form sodium citrate. So we have interactions, and remember we specified that the salt is really concentrated, right? Because we have an aqueous solution, so everything should ionize. But if we put in a ton of sodium, it's going to start disrupting this network, right? And so
So is the citrate still tapping around, or is it causing it to remove that?
yeah, so if we put in enough sodium, we can saturate the solution of sodium citrate and get it so concentrated that it starts to crash out. And then once it gets there, you don't have enough citrate capping the nanoparticles together, so then they can start growing and finding each other. Have you ever seen like cold welding or something like that? So if you have two metal bars in a vacuum, and you know they're two chunks of metal, you just touch them together and they form a single bar of metal. And this, it has to be in a vacuum, right? Because you can't have any oxide on the surface. But the metal atoms in this bar and the metal atoms in this bar don't know that they're different. So whenever you bring them together, it just forms a metal, right? And so this is kind of the same thing that's happening here, where things are growing by touching. So once they come into contact with each other, it's now bigger. It's now a bigger thing. So that's something interesting about metals, is that the bonding in between metals is a lot different than the bonding in, like, you know, a molecule, like an organic molecule, right? Where you need electrons to actually move around. It's just everything is metallic, everything is in the zero oxidation state. So as soon as they touch each other, well, now you have a bigger thing.
So we're promoting growth, so we're just basically forcing it to. I see, interesting.
I'm gonna see if I can find like a animation of this actually, because it's really cool if you haven't seen it.
I'm gonna take a little break, go outside.
Sure.
The mask break.
So what was the point of making this again?
So the soap is like a surfactant molecule. So basically, in that one we added the soap and then we added salt. But then for the other one, this one we just added salt, and that's what caused it to crash out and have little floaty particles, and we no longer have the ruby red color, right? And so then this one, the soap was actually able to protect the.
It's basically a coating.
I see,
Yeah.
I see.
Yeah, so I drew it on one of these, but you can see how small the citrate is, right? It's just only a few atoms wide. The soap is this giant thing, depending on exactly what molecule the soap is, right? You have maybe 20 atoms here, so it's extending a lot further out from each particle, so there's a lot more distance between them.
So we do this to, like you said, to conserve the individual ones that we captured, right?
And so the color is the same because they haven't grown anymore.
Yeah,
So we seen the one we just made. Which one was it? This one?
blue one.
This grew because we broke down the citrate, right?
So think about it. So the first thing we made, the ruby red, was a nanosphere. So basically one diameter, right? And then we're making nanostars, where basically there's rods growing in different directions. And so they're depending on the length of that rod and what, like, it's going to interact with a different wavelength of light than the single sphere would.
Okay, I get that much. So we took.
Yeah, so like they'll go in maybe one direction and be a certain length, and then one might be a different, and so that like nanometer length is going to interact with a different wavelength of light. And then it's a little more complex than just the sphere, but that ends up making it a blue color.
You can actually watch different chunks of metal touch each other and instantly.
Yeah, it's like, no, wait.
It's not like you can still see like a join between them where there's some separation. As soon as they touch, all of the atoms are like, oh, I'm
Like
now
this, so
part
like
of this extended
if
metal.
this were, yeah, it's
And
like adding
it
on.
happens as soon as they
So it
touch.
is growing.
And so that's
And we're adding more
happening
gold
in our
too, so it kind of
nanoparticles,
makes
just
sense.
atom by atom.
It's not
As soon as
reshaped.
another atom finds
Yeah.
a growing nanoparticle, it's like, okay, I'm part of this now. And then if we have two nanoparticles touch each other without that capping agent, then they grow.
I see.
And so I think we talked about this later. This is actually yeah, so if we go a couple pages further,
the process of this. Let's see.
so this is what I was talking about where you have a nanoparticle that sees other nanoparticles and continues to grow. But you can see it actually makes kind of a distribution. So instead of having, if we say this is
You're getting that optimized.
what we want when we make nanoparticles.
Somehow it encourages
Some of them we did where we'd add it and it would like take a while, but then when we repeated it, we would
Because that's going to give us uniform
like, oh, what's going on?
This thing is this color because all of the nanoparticles are the same size.
Like, how fast do they
If this process starts to happen, you can see you have something big that starts to decompose and then add to it.
It might be something that we're putting in the seeds, right? Maybe it's just something that like stimulates the like nucleation from the seed.
So now you have, instead of this one size, you have things that are way smaller and way bigger. And that kills whatever you are trying to get out of a nanoparticle it originates from it all being the same size. So this kills the functionality of whatever you have. It wouldn't be the same color, it wouldn't have the same kind of plasma resonance that you have inside of it. And so yeah. So the size of our nanoparticle is what determines if we have a larger particle it's going to absorb different magnetics than smaller. And I think we're about to get into that. This effect depends on everything else inside.
Yeah, I don't.
It's like a whole
I don't know.
every single thing needs to be in phase.
We're adding this acid, we're adding silver nitrate.
It'd be like that. And you have every single swing to be
What's the purpose of adding
but
these?
then you have one swing that's like
How does that prep?
way shorter, so you gotta
I believe they're all shaping agents, but I'm not 100% sure, and I don't know which role they each play. That's a good question.
I was just curious.
Yeah.
yeah, that's pretty good.
Yes.
So we didn't really get to focus on it earlier, but you can see the soap up at the top. Put the soap in and it protects everything. So it keeps things from crashing.
All right, everyone, can I get your attention, please? So we actually have one final experiment to do, so I want to kind of move us along so that we have enough time to do all of them. So one thing that I do want to mention, though, because I kind of forgot to mention this, you have an extra sheet that you might have noticed in your packet. So that is something. Thank you for the mic. That is something that I kind of added to show you guys just a little bit when you can start thinking about, as instructors, how you're going to do this. That there is some stuff behind the scenes like that we labeled ahead of time. So that was just kind of showing you like you might want to have students do that a period before, or you can do it whatever works best for your schedule, really. And then another thing that I want to kind of revisit really quickly because I saw some questions about it. Returning back to the surfactant example where we added the soap, one thing that you might notice is that if you added salts to that after you added the soap, unlike the first example where it caused it to crash out, the salt doesn't really do anything if you've added soap first. And the reason for that is once you've substituted what this surfactant is, the mechanism by which it is using to keep the particles apart is different. So for the citrate, you had this kind of electrostatic repulsion where you have, more negative charges wanting to repel the negative charges on the citrate ions of the other particles. But once you have these kind of like hydrophobic tails, the ions themselves aren't really doing anything. The ions aren't going to draw those closer together, which is what the influx of sodium was doing. So that's kind of the difference there and why you would notice a difference if you added salt after adding the soap. Okay, so I was walking around and I saw some very, very pretty synthesis. So
this is sort of an example of what you guys wound up with. And some of you I saw holding your solutions up to the window, some people putting it on top of a phone light to really see that sapphire, that hue, I think is very pretty. And so this is the spectra of what we're looking at. And one thing that you might notice is we actually still have this sort of absorbance in the green that we had for the first one. But now what we also have is this absorbance at 837, this peak here, and that's going to be the reds. So sort of what we're left with is what's not being absorbed, which is here are blues. So that is why we have blue nanoparticles. And yeah, to reiterate, this is all just still gold. It's just a different shape of gold, and it's changing the way it's interacting with the light because of the dimensions of these shapes matching the visible wavelengths. So very cool stuff. All right, so the last part of our, oh yeah, and this is kind of just reiterating that we're seeing the absorption of, we're seeing what is not being absorbed in this case. So the next part of this experiment is going to be looking at another aspect of particles and something known as scattering. So this is something that I personally, admittedly, find probably the most complicated to explain because we've been talking about absorbance and these colors this whole time as being, we're seeing what's not being absorbed. So let's kind of back up a little bit and talk about what scattering is. So an example that I thought was really cool is this picture here of a block of ice on top of snow, because it's a similar idea. In terms of chemical and molecular compound-wise, the snow and the ice are made out of the same thing, and they are, solid phase of the water. But in the case of this ice, we can see through it. It's just the light is passing through easily. But in the case of the snow, we have this white. And that is because the snow, these particles, are scattering. So what happens when you have a bunch of these randomly arranged particles is that light can essentially bounce off of them and go in all directions more randomly. And so scattering is something that occurs related to size. You need small particles. Okay, yeah, that's scattered light, incoming light. And it's something that is also going to be occurring with our nanoparticles. So what we're going to be doing is growing them to be a little bit larger so that you can start to see this phenomenon. And an example in art history, I mentioned the Lycurgus cup, and this is something very cool that people didn't really understand why this was happening, but I'm glad that we kept it in such good condition all these years. If you put the light inside the cup, so like the light bulb inside of it, then you're purely seeing the light that isn't being absorbed, and you see the red, really similar to our particles. But if you were to put the light on the outside of the cup at the same vantage point that you're looking at it, you're actually seeing a lot of the scattering back, and it's that same wavelength. So unlike it being absorbed, you're now seeing it randomly have this probability of scattering back at you, and so you're actually seeing the green. So in terms of physics, understanding scattering and why it happens with larger particles, it can be a very complicated equation that has to do with the phase of light and can be very complicated in terms of the physics. But I think that the best model for us to understand it is that when you have these bigger particles, you have these sort of random events where the light is interacting with these electromagnetic fields of now the electrons oscillating, and that has the probability of that light actually just coming back at you at that same wavelength. And that is what the phenomenon of scattering is. So in this last experiment, it's pretty brief, but you're going to be using some of your original solution and adding a few extra reagents, including some more gold, to grow these up. And then you're going to be seeing if you can see the difference in the color you're observing based on where you're holding the flask in relation to you. So I think you guys are pouring out the solutions.
Okay, yeah, they're almost done setting up, but we'll be coming around giving you guys the solutions that you can do this to modify your gold.
If you were inside the cup,
Oh, yeah.
sitting inside the cup, like from the inside of the cup, if I was in there, would I see green scatter? So, if I'm standing inside the cup, shining the light from the inside, yes, will I see green? Exactly. Which is very strange, because probably, yeah, you just shifted your perspective because it's standing by in front of the cup, it would look green to you. And so some people made this for the
Because they definitely.
Yeah. Basically make a bigger by, we added the soap here, so we had a bigger, I don't know how to describe it.
So you're on the right track, but it can get dangerous to use the term bigger because whenever we're talking about size, we're talking about the size of the nanoparticle.
Correct.
Right? Whenever we put the soap in, we make the whole system bigger, but
Yes.
what's actually absorbing and scattering light?
It's the size of
Yes,
the
it's the nanoparticle in the center, right?
Yeah.
So even though you have this really big thing shielding it,
Yes.
the actual optics haven't changed, right?
Yeah, it stays the same, right?
Yeah.
Yeah,
And so
we haven't,
what we were doing in experiment 2 is seeing, okay, we have these nanoparticles that are stable because they're capped, right? And they're capped so they don't see each other and continue to grow. How can we disrupt that or make it more stable? So we said, okay, we can disrupt it if we put in salt because the only thing shielding it is this negative charge. And so we put in a bunch of positive sodium cations. We disrupt the ion shell that's protecting our nanoparticle, and then it all comes together. But if we put in the soap, instead of just having ions surrounding our nanoparticle, we now have like a physical barrier, right? Because we have this 20 chain carbon long shell surrounding the nanoparticle, so now they physically cannot interact. So even if we put in salt, the mechanism by which they're stabilized is different, right? And so now we were talking about this earlier, right? What if we just put more gold in?
Yeah.
What is solution E?
Is it E?
Yeah. Yep. So that's our gold 3 solution. I think it's a different concentration than we had earlier in solution A. That's why
it's
there's
more concentrated.
yes, it's more concentrated. Yeah, like 4 times as concentrated.
So it's absorbent.
Okay,
But
so
this
yeah,
one is absorbent.
you can definitely see that solution E is more concentrated than A, right?
It's a
It's a little
stronger
darker.
yellow.
Yeah. It's that lemon lime Gatorade color.
It's a hard straw.
Yeah.
A soft straw.
Yeah. Of course. Yeah, and so let's just start following along with the procedure. No, we still want to be careful that we're using clean. Yeah. And then in your class, you can just rinse things, right?
Yeah. You'll have.
So if we need more,
Do we need more?
Is there a preference in our class? What type of water?
we need 2 cylinders. I think it's distilled. Yeah.
Water. I said bottle.
Do we need more graduated
Yeah,
students?
I think we need 2 here.
Here you go.
The water in this is distilled, right?
Yeah.
Correct.
Yeah. That just keeps additional ions from messing our stuff up.
All right, let's do it. 6.5 solution.
we have clean scent vials.
Here's the stick.
What's up?
So we need vial growth 3.
Yeah.
Yeah.
So we got some vials over there. Just make sure they're
labeled.
labeled, yeah.
Is that growth 3?
Yeah.
Yeah, so we already got our 6.5.
Yep.
They went through the straws.
So we're gonna put that into a vial.
So just label.
Yeah.
Yeah. Make them.
This is gonna be our vial B. You have the marker.
Where'd the marker go?
So
We definitely had one.
But I was like, biohazard.
we'll find it in the meantime.
There you go.
The one part that I don't know if we like had all the stuff because we kind of jumped into it faster.
Yeah,
I didn't talk for as long as I did for the other one.
Justin's coming in a bit, right? Is that the next part?
Yeah. So we're gonna return first to the mental model from the demo, and then
What did I call this?
Cool.
Right. Right over it.
Just
Single line mark through.
Yep. Call this growth
Growth 3.
growth 3.
Oh, do we need a stir bar?
yes, you do. Do we not have our? Oh.
Can we reuse or no?
Steps, I know.
But I mean, I wonder how long this would take. Wow.
Depends on the students.
I mean, but this is not a single lab.
Yeah, it definitely could be like maybe a thing where it's more of like a project style lab where you take it over multiple
I mean,
days.
if I were to teach it, if I were to do this with my students, I'd separate it.
Yeah, right, for each experiment, yeah. When I was in high school, we had block periods, so we had like more time per class, but it wasn't every day, which was helpful for labs. But yeah, you'd have to adapt it based on how much time you have.
Okay, I think we just gotta fish the stir bar out.
Yeah.
Oh, yay! Yay! There you go.
Really appreciate you making
Use a syringe labeled solution out.
Yeah, and so let's get that growth 3 going on the stir plate. Once you get the stir bar in there. Is that growth 3?
It is growth 3, but we don't need an Erlenmeyer.
Yeah. So no, it's in the scintillation vial,
Measure 5 milliliters.
and then we can get that stirring.
Heat or no heat?
No heat. It is plastic, so we
Yeah,
don't wanna-
that's why I was
Yeah, yeah.
hesitant.
E?
Nice, nice. Okay. So now we just have a ton of gold in there.
Yeah.
And we're gonna do it's basically the same synthesis as before, right? But now we have more concentrated gold. We have more sodium citrate.
Syringe. I can use this guy. Have a good day.
Grace out. Oh, yo, double lunch.
Which one are we doing? Solution G?
Solution G.
Might have been
Did you add 0.4 mils of solution F into here? Okay, yeah, make sure you do that. Remember, F is our capping agent, right? And it's our reductant.
So adding this into that.
Yeah. And F is the citrate.
Got it. With sodium.
It can stay stirring.
It can stay there.
Yeah, yeah. We've been doing 3 sessions a week, and then we have games on the weekend. We're starting, I think we play USC this weekend.
Oh, that's fun. A rival.
Oh, yeah.
And like that.
We're gonna do this. No mercy.
I need to take out the air bubbles.
Oh, please do. Just like all like ruined out.
Foam fingers.
You have G ready?
So we're putting 0.4 mils of solution F into this one, right? You ready for lunch? Yeah, I'm getting there. That yogurt's only gonna keep me going for so long.
I'm running on straight caffeine.
Oh yeah.
Yeah. That's why I'm wired right now.
And that was the
Solution.
that was such a okay, cool.
And so remember the last time we made our nanoparticles? As soon as we put in the citrate, it went clear and then started growing, right?
Yes.
So what does this indicate to you that it's still yellow and nothing's happening?
It's taking a while because there's the war.
Okay, so it could be kinetics, right? It could just be that it's taking longer. But notice we have a lot of gold, right? It's like very concentrated, and we didn't really put in that much citrate. And remember, the nanoparticles only start growing once everything is in the 0 oxidation state, right? So we haven't put in quite enough to let us start growing nanoparticles because our gold is still +3 or +2 or +1, right? It's still charged.
Sure.
And reduced by citrate.
Yeah. But yeah, then so now look, we're putting in a ton of solution G, right? And solution G is another reducing agent, ascorbic acid. So it's going to have a positively charged thing and negatively charged thing. All right, so we're measuring out G now.
Oh.
Yeah. So, no.
Okay.
I think because this one's just going to get so big, like it doesn't have to all go at the same time and get that super narrow distribution. Because I think, so I said I thought we were like 100 nanometers. The first ones were like 5 to 10. So those are super small. So if you have like a big variance, it's going to kill the optics. But if this is like 90 to 110,
right?
it's going to be about the same.
Oh, so you did it already.
Okay, cool. So then you guys want your seeds, right? So those are the ones you've already created. Your nanoparticles.
They're gorgeous, ruby. Yeah, so very little, right?
Right.
And that's because this isn't the entire stock, right? We have a bunch of gold in here already.
Yeah.
This is just our seeds for it to grow onto.
So you have to just measure 0.12?
Yeah, so it's going to be a very small amount. Bebopping. What are you doing after this?
I think it's less than that.
My brakes are messed with my car, so I should try to find a place to put it. But everywhere I've looked closes at 2 p.m. So
Just do it yourself. It's easy. I've changed the brakes.
I don't have brakes.
I don't have brakes.
I think my rotors are like I think
Yeah,
I need to replace.
yeah, you got to replace the rotors and the pads.
I don't have any of that.
So what you need a caliper expansion tool.
Okay, check.
Because you got to compress the brake pistons. Then you're going to insert your new pads, put on your new rotors. Make sure you have all the brake hardware.
Yep.
So this one, since it's such a small volume, probably the easiest way is to just, this is what you're using, right? Yeah. So if you're at such a small volume, I wouldn't worry about the air bubble at the top.
What?
What's the deal with the?
I would just pull up the
They're
top
like they want me to.
and then push it
I
out.
might have to take Monday morning off.
Try and get it wherever it's on.
Well, it's not so bad
see I have that air bubble at the top? I'm just going to follow that. So there. Because you're going to be flicking out those two.
A little fast and loose with the syringe technique, but as long as you're consistent.
So we're gonna add that to.
Just don't tell Arlene.
So we're
Miss
gonna
Russell.
add seed, and we're gonna transfer it to G3.
Dr.
right?
Russell.
What a sweet woman. Did you ever
Yeah,
watch
I guess
Adventure
so.
Time?
Sweet woman, but we gotta
So
make
add
those
the
meetings
content-
more pressing.
Did you ever watch Adventure Time?
I think so. That's
Oh
supposed
yes,
to
yes,
Named
and then
Tree
we're gonna add
Trunks.
that. We're gonna add this, and we're gonna, I think we're gonna completely add that to that.
Okay.
All right. So, yep.
So we're not waiting for it to do anything else, right?
Just add it.
Go for it.
Herself as such. ITA for her. A lot of times in meetings.
So we've added our seeds, and it started out as kind of like a little red, and it's faint orange, and we'll see what happens as it grows.
And then we add all of the absorbent
And so,
acid.
so remember how fast the reaction happened when we were
Yeah.
boiling? Happened
Yeah.
super quick, right?
Right, yeah.
And so now we're just at room temperature, so there's less energy in the system, so it can't grow as fast. But we do have a ton of gold in there, a lot of reductant, right? We have all this acid in there. So we should have all the things that we need to let this stuff grow. It's just going to take a little bit of time. You gotta stir it
Stir the
up.
pot.
Add the contents. Do we wait or do we add it?
Yeah, I think we've added everything that we.
Oh,
The
wait, no,
absorbent
we
acid,
haven't
no, we're
added
still
any.
waiting on
Oh,
that.
oh,
Do we
yeah.
add it
Makes
all,
sense.
or do we only add
It says all, I think.
All of it, yeah.
Yep.
That makes sense.
Okay.
I was like, yeah, it's still pretty light. So it's not growing because we haven't added all of our reductant yet,
Yeah.
right? We have to
Yeah.
get all the gold from +3 to 0. So this
Yeah.
this should do
So
it.
you just add all of
Yeah.
it?
Yep. Nice.
Okay, so see, as soon as we have enough in there for it to go from +3 to 0, then the gold can start to add onto itself, get bigger and bigger and bigger. Ooh.
There you go, your
What
white
does it
light.
look like over there?
What does it look like?
Like on the other side.
Yeah.
Say it again?
Anything?
this? So the ruby color, that's what I see. I don't know. Could be magenta.
It looks a little cloudy. Is that just
Yeah, it does look a little cloudy.
There you go. Yeah, it does look cloudy like cranberry juice.
Ah, yes. Does that mean we messed up somewhere?
No, I think it just takes a bit to grow. I mean, if you look around at other people, it's like
Yeah.
it just gets darker.
It does say
because
wait a
it's
few
gonna get bigger.
minutes.
Yeah.
So how come this one we're not being a little more aggressive with the stirring and temperature?
So, whenever we have smaller particles, the size distribution is more important to control, right? Because, okay, so if we have, say that we're doing this at room temperature, so things are growing at slightly different rates. So in the end, we end up with like plus or minus 10 nanometers, right? So 100 plus or minus 10, you go 90 to 110. The stuff that we had in here is like 10 to 15 nanometers. So if we have that kind of range, we have like 100% difference between different particles. So things are like double in size of the others. So whenever you're trying to be smaller, you have to make more things go right. And so whenever we put all that energy into the system and boil it, what we're letting happen is we want everything to start growing at the same time and at the same rate. Since we're at room temperature, you know, think of just like activation energy, right? So some things are going to have enough energy to go over and do our growing reaction. Some things won't, but it's always changing over time, right? If we're boiling it, everything's going over. Right? So we just have a different thermodynamic population in our vial now. Let's see if.
Are you freezing too?
Are you freezing too?
Yeah, I get cold
I'm
super
shivering.
easily.
Like, yeah.
This building is notoriously cold.
Ooh.
Okay, so it's like pink.
That I saw. I was outside.
And then here it's like much darker.
What color are we aiming for?
I actually don't remember this part.
I think supposedly. So remember when we talked about the historical application
So
of
this-
gold nanoparticles, where there's like that cup.
So if you
That
look in line with it, it actually
shallot.
looks kind of orange,
What?
right? It-
Yeah. That's what it's
So
called.
if you
I
come
didn't
around
ask
and
the
look
name.
at it,
Um,
yeah,
the
it,
other
When you're
it looks
looking
rusty,
at it, it
right?
looks red, like when you're
So if
just
you come
illuminating
and look
it, but then
right
when
where
you,
I'm shining the
when you
light,
put the light,
it looks kind of
and then
rust
it's-
colored
yeah,
or
it does.
orange.
Right, right.
And then on the other side, it's like purple. So if you were over here, it looks like dark orange.
Yeah.
Oh,
Yeah.
So it's much different. And so the light that we see over here is the stuff that's getting scattered. And the stuff that's getting scattered is telling us something about how big the particles are. Same as our emission.
So light's getting scattered here and then on the other side.
That's the plasmon resonance that you're seeing on the other side.
is that because the source is?
Yeah, and so the stuff that you see coming back to you is the stuff that's not getting absorbed, right? It's the stuff that's getting, like, bounced off.
Bigger, so light comes in.
All right, I think it's probably done growing. It looks pretty stable now. Ooh, I'm hungry.
I know, right?
What did y'all get for lunch? I got the caprese. Oh yeah.
Hopefully I had fresh mozzarella. That's what tops it off.
I feel like I will send this back if it's not.
Mozzarella.
What'd you say?
This is not that.
Before that.
Let me repeat what I just said in a weird
Yeah,
voice.
yeah.
Do we know where they're from? The food?
Absolutely.
Trying to like look at the logo on the bag, but I can't really
Subway.
decipher. No, don't say Subway. Don't say Subway. That would be.
Cursed.
I don't want Subway.
Which program did you come into?
So I'm in the chemistry and biochemistry department on
Apply
the,
directly to chemical.
yeah, and then there's like specialization. So I'm on like the materials. Yeah.
Material is the coolest one.
Yeah, it is. Most people here are probably materials.
A lot of people
Yeah.
here are in like the Tolbert lab,
Yeah.
which is the battery material group.
Length of it also kind of
I did my grad school. I got my PhD here many eons ago.
Was Sarah here?
Yes, she was.
Was she still doing laser stuff?
I don't know. I was in the cryo EM.
We have like
I was doing.
we have like 3 laser tables in our lab, and they're all just used as storage.
Oh, that's so funny.
Just like multiple thousands of dollars for these advanced tables, and we're just like, yeah, that we could put a box on there.
Oh my god. So do you have to do rotations through labs?
Yeah, so I'm like on my, so I did like a summer rotation, and so now I'm on my like first fall rotation.
The one where you get nothing done.
Yeah, that's true. But it just, because you're taking
classes.
classes
Right,
and
right,
everything.
And teaching.
And teaching, yeah. But
Teaching was first
My
year.
brain is
Yeah.
scattering right now.
now
It
it
might,
is, I don't know.
yeah,
But back then it was the second year.
that sounds better.
Yeah, that does
good.
sound,
The first year is
It's brutal.
It's hellish.
Brutal.
yeah. I'm glad I'm teaching like lab sections, which I feel like is a little bit, the like first quarter of organic lab is what I'm, yeah.
But you're lucky because you have actual chemists.
Yeah, I have like the majors
Yeah.
rather than the
I always,
pre-meds.
all the classes I've taught were for pre-meds, and so it's like,
More about the grade than the chemistry. Yeah.
I was micro. I love doing micro labs.
That's cool.
Yeah, a lifetime ago. I graduated in 03.
Okay.
which I mean that was just temporary, it was transient. I have kids at home.
Yeah.
So trying to get back into science. Yeah.
Oh, there's Andrew again complaining.
What did you do undergrad?
What did I do?
I'm just trying to make
Oh,
sense of
Claremont McKenna.
all of you guys.
It's like a small school. Yeah.
So the wavelength that things scatter is dependent on their size, in the same way that the wavelength that they do plasmon resonance at is dependent on their size.
So when we do these, they're still mostly red, but you could see that they changed the color a little bit. Like they're not quite the same ruby, like that lighter. So they're a little different. We made them bigger, but now that same wavelength is also more intensely scattered.
Oh, because we increased the size of the nanoparticles, right?
Exactly.
And that was due to all the acids we were dumping in there.
Yeah, we just have more gold. We have more gold.
Ah, I see. So more gold meaning light was scattered more?
Well, we put in more gold because, so what do we call these things? We call them seeds, right?
Seeds, right?
So they start as something small, and then we put in a lot of gold and a lot of reducing agents. So the gold 3 turns into gold 0, and once it's gold 0, it can start growing and growing and growing and growing.
Right? So we basically have bigger nanoparticles, right? Because they're all accumulating.
They're still nano, yeah, but they're much bigger now.
Yes, much bigger, and that means that light isn't passing through as well as it should.
Right, yeah. It's the same thing with snow and ice, right? So snow is like up bigger, like you can see an ice crystal.
Yes. So
Polarization of the light. So that has to do with the plasmon resonance, but things don't have to be polarizable to be scattered. Right? You can scatter off of just something completely inert as long as it's the right wavelength, as long as it's the right size. I think it still has the same polarization, but because it's bigger, you need longer frequencies because the electrons have to travel more distance, so it's slower. But it's still gold, right? It's still a metal, so the electrons can still move. So I think that's kind of like a bulk property, right? So how electrons can travel through gold atoms is kind of the same no matter what size it is. But the exact size determines the frequency of light that will do the plasmon resonance, because you have to move things. So the longer distance that you have to go, the slower it'll be.
there's a lot of terms going on here. So the light's hitting this, right? Light is being absorbed.
And so what you see is the stuff that's left over, right?
What we see is what didn't get filtered.
You want?
Right.
Thank you.
But that frequency that is absorbed is what gets scattered back at you.
This way or that way?
So whenever we had the light source like going this way, remember it looked like orange coming back at us.
I'll wait. All right. Yeah, I know it's been a lot of morning, and there's a lot to digest, and we're gonna be here, throughout some of the afternoon, so we can keep talking about this stuff and really working on like ways of wrapping your mind around it, models that make sense. But sort of to just describe in schematics what you did. You had your original gold. Oh, thanks, Mark. You had your original gold nanoparticles, which it turns out if we were to look at these under the microscope, they're pretty small. They're on the order of about 12 nanometers it's a rather precise number, but on average they're pretty much in the order of tens. We dumped more gold and more citrate because we need even more capping agent if we're growing them, and we grew them up to be more on the order of hundreds of nanometers. So what some of you guys were noticing and finding different ways of orienting maybe a phone light or a flashlight, or even looking at it in the sun, trying to see how you can observe the scattering. And so this is something that I was also discussing with the grad students. One of the aspects of this is that the bigger the particles are, the more of the light gets scattered as opposed to being absorbed. So there's a couple things. Concentration can be one of them. You can imagine if you had just a very thin layer of this solution, it might be kind of hard to see, whereas if you have like a big vial of it, it's going to be a lot easier to get that light to kind of scatter back at you. But as an example, if you have just a molecule, when this energy is coming into it, you're going to have energy transitions. All that light is going to be absorbed. You're not going to get scattering off of a molecule. As you start to go a little bit bigger, now you have nanoparticles, there is a small amount of the light that is scattered. So even with your small nanoparticles that you made originally, there is technically some of that light that is scattered back at you, but it's not a lot of it. So the intensity is not something that you can really observe. If you had like a very good camera or spectrometer, you might be able to measure it at a different orientation, but it would be very weak. But then as you start to get to these bigger nanoparticles, you know, on the order of, you know, over 60, more to the hundreds, you're going to start seeing that a lot of it is actually scattered, but you still have that absorption. So one of the things you guys probably noticed is that your solutions were still generally red. If you were to hold them, you know, with the transmission, the light passing through it, you know, they're kind of like a nice plum color. And that's because they're still spheres. We've shifted the wavelengths a little bit because of the size, but then not all of the light is being absorbed. A lot of it is actually scattering, and you can see this based on where you're holding it in reference to where the light source is. So it's a little bit of a trick, but hopefully you guys were able to observe that. There is a limit to this, so as you can imagine, specifically for the gold and what's giving it this color, if we started to go to, you know, hundreds and hundreds of nanometers and then, you know, micron scale gold, we would actually lose this plasmon resonance because we wouldn't be able to achieve this electron harmonious oscillation because the particle would be too big and not the same order as the wavelength of light. So there is a limit to this when it comes to gold. But then you might notice like other particles, like milk is another example. You have scattering because there's actually like small kind of like particulate clusters of things in milk, like the fats and other oils, that's causing scattering in that solution. And that's why it looks white to us, as opposed to being like just a clear liquid.
But it's not scattering
Yeah, so it's not, the reason that it looks white is because it's just all of the visible light is kind of just coming back at random directions, and that's why it just looks white to us, as opposed to this, which has a very specific wavelength that it's interacting with, and that's why it's, you know, the red or the converse green that we see. So that's sort of the nano size dependence of why we see like the strong colors with the noble metal nanoparticles. So in that case, that would be if the individual crystals are more, you know, maybe micron scale, so they're a little bigger, they're not nanocrystal. I mean, I imagine you could grow nanocrystals of snow, but naturally, you know, it's a little bit bigger, so you're getting sort of like the collective scattering of all those wavelengths just randomly going back in all directions towards you. When you see like a big chunk of ice, so there's also like a really nice explanation I thought that was written in the manual that we'll be providing for you guys, like the teacher's manual. With the ice, like a big chunk, you just have one. So you don't have this many different randomly arranged particles, whereas the snow, you have many of these things, and so when the light is going at all directions from each one of those, it ends up being a scattering effect. Whereas with the ice, it's kind of just passing through, and you're not getting this random, all directions light back at you, if that makes sense. So it's sort of It's a property that it's a phenomenon that requires you to have a lot of particles, and also the size of it will influence how much of it is scattered to you. So, you know, hypothetically, I could imagine if you had a lot of ice cubes and you were able to somehow see wavelengths of a much, much bigger size, and that was what we saw, you probably would have a scattering from ice cubes. But it's not really something that we perceive or interact with those energies. They would be very low energy. So it's kind of a funny way of like thinking about it, but yeah.
But if you rough the edges of ice, you get the same thing that you get from snow because you break it up.
That's a good point, yeah. So if you rough the sides of ice, then suddenly you have all these non-uniformities, and then each one of those points, if light is going from all directions from each of those randomly at you, yeah, it's gonna look white. Or like yeah, impurities in ice too. If you're like me and your ice tray is kind of dirty, you can see like, oh, those ice cubes look white. That's weird. Usually toss those ones. But yeah, so the last thing that I want to kind of end on before we transition really quickly back to our, it looks like lunch is also arriving here. Before we transition to recapping our mental model, and Jeanette's going to kind of take it back for me, is just talking about a few applications. And also Justin is here, who's going to be giving our guest lecture. So one thing that we mentioned right at the beginning is that where does all this energy go? So when you tend to get these resonances, these particles can get very, very hot, especially relative to their size. So one application that people are actually looking into is a method for not chemotherapies, but something that we're calling photothermal therapies. So if you're able to direct, for instance, a gold nanoparticle, probably in conjunction with some sort of specific biological recognition unit, like an antibody, and get these particles to target certain cells or areas of the body. Cancerous tumors might be expressing a protein that you can target with an antibody. The goal would be to get these particles to go to that specific site as opposed to healthy cells, and then apply the specific wavelength that we know that that size of particle will resonate with to generate a very local, very hot spot to actually just kill selective cells that we're interested in targeting. So that is an example, and this is some research that people are actually conducting on this stuff. So yeah, pretty cool. And nanoparticles actually are in a variety of other like consumer products that we use. So sunscreens as well is another thing, slightly different. I think people use titanium. But a lot of these small nanoparticles are surprisingly safe for the human body. So a lot of interesting research. And in our guest lecture, you'll hear a totally different type of application that has to do with looking at different absorbance wavelengths, or not absorbance wavelengths, different transition energies, and how we can use that for imaging. So last but not least, the take-home message is we're dealing with nanotechnology. These particles are very, very small. So the fact that we even see these phenomena so brightly is pretty remarkable, I think. But it is kind of a secondary observation where light has to interact with it first, and then we see the results of that interaction. So the other thing that we looked at was plasmonics, and this phenomena is specific to metals. The reason for that, again, had to do with the fact that these metals have these electrons that are not localized when you have the neutral metals, not the ions, and they come together to form these particles. The plasmons themselves are then the collective oscillations, when you can get all of the electrons in that particle to oscillate to one side and then the other. And this is also something that is fun for us because we see the visible wavelengths, that the size of those particles are the same order as the wavelengths we can see. And that's why we're getting these cool colors that we can appreciate. And then lastly, we actually are using, aside from the art history examples that I showed, you can use metal nanoparticles for some of these properties, not just the visible things, but the heat that they also are going to generate. So if you were to take, a laser, a really intense light source, match it to that resonance frequency, you actually get very, very hot. So that's it for this part of the presentation. And yeah, thank you guys so much. Question quick? So that's a good question. So mechanically, it would not be possible. You could probably get like small micron size, but the nanoparticles, especially the 12 nanometer ones, are so tiny. It's a very small, collection of atoms that come together. And the only real way to do that is to control, the ratios of the reagents and know how we're adding them together to get them to be just that small.
I gotta tell you, it's not right. You can ball mill. You can actually make nano-sized objects.
Wait, really?
Yeah, you can just grind. There's these things called ball mills where they have big grinding mills, and then it's basically like the way you polish rocks. Right? You just sort of do this over and over again. So it does work. It just sucks. Sorry.
Well, there you go.
They're like the same size things. You want all of them to be the same size, and that's why you use them.
Okay. Well, thank you. That's good to know. It could have
I
been.
don't think it was.
I think they heated it.
I think it was a gold salt that they heated up.
Yeah. Okay, the last thing I'm going to mention before oh no, thank you for adding that, because I don't want to give you guys the wrong information. The last thing I want to mention, especially when it comes to planning this experiment for the class, is that these particles are actually surprisingly stable as long as they have those capping agents. So especially like the first solution that you made in part 1, this nice ruby one in the Erlenmeyers, that can keep. So I would say even like months, if you store it well. And
I have some in my office from the last time we did this workshop. And
which was
still,
2 years ago?
They're still sitting there, yeah.
Yeah, so as
they're
long
very
as
stable.
you keep them, prevent stuff from just falling in there, don't mix any acids in there, or any salts, that's the big one. They should be good. So you can kind of pace this over, a couple days, weeks, even, I guess, 2 years
Yeah,
to
quite a while.
revisit it. And so we also, if you guys don't want to, fight over them, decide amongst your tables you can keep these and take them home. So we can also give you guys extra scintillation vials if you want to split them up. Yeah.
Nice. And I hate to be the mean timekeeper, but we've got to move on to the next part. But while our speaker is setting up, that does give us a little bit of time to work on the next draft of our model. So if our speaker would come up, we can have him set up, and then I'll turn it quickly to you.
Yeah. Okay, so we are actually going to we're going to work on the flip side of our explanation from the part 1.
I know. Well, the red one, the blue one isn't good anymore, but the red one is still there.
Yeah.
The first one. Yeah, it's surprisingly stable.
No, it's okay. So try not to modify your original explanation.
Yeah. I think so.
Do you have a new connection?
Let's try some stuff here. So what I need is. Nope. Okay. Oh, it's just a few.
Which one do you need?
No, it's fine. I got the. Thought I had brought it. Oh, wait. Hold on.
We've got more adapters in the office if you need it. Whoops, sorry.
Alright, let's try this out.
Oh, you've got that.
Yeah, of course.
So if this doesn't work, then I think I've got a VGA to
To
USB 3.
USB 3.
whatever it is.
Oh, sorry, this might fall off. So.
But, oh, that works.
Oh, we're up.
Yep.
Oh, great. It's been a while since I've given a public lecture.
Really?
Like I've done online lectures, like
Sure.
plenty of online lectures, but I'm teaching now, so I guess that counts. But
but that's not public technically.
Yeah.
Well, thank you for making this your first one.
Well, no problem. How are you doing? How are things going otherwise?
Good. I mean, you know, we were doing virtual workshops through the pandemic, but this one really
This is your
can't
first
be done.
in-person, yeah.
Yeah, so this is our first in-person one.
Great, great.
So-
That's good.
Yeah, and it went really well. All their stuff synthesized nicely, and it's a pretty robust, replicatable experiment. So
Yeah, that's great. And so they
Yeah.
get to take like kids back to their lab, to their school. That's really cool.
yeah.
I think we're good. Like, they are all put on top of the house, so whenever you're ready.
Okay.
We're always trying to do stuff.
So if you want to collect them and then give them to Lee, then she can look through their explanations.
This is I'm not used to the N95 mask.
Yeah, it's a little.
They're like always so.
A little
They're hard with glasses too.
Oh, I bet. Yeah.
That's
Do,
good
do you
practice.
get the fogging?
Yeah, I just have never. Honestly, I've been lazy. I've just been wearing the cloth masks everywhere.
I mean, you're vaccinated, right?
Yeah,
So
yeah.
it's
Yeah, you have to be.
fine. Yeah, I mean, that's true. To be here, you
To
do
be
have
here,
to
you have to be. Yeah.
Unless you have a, well, you could have had a medical exemption. I don't know.
No, I was definitely I was desperate to get it as soon as I possibly
I know,
could.
right? Me
I
too.
drove out to like I got mine at Magic Mountain. So
Oh,
I drove out to
really?
Magic Mountain. We waited, and I got it while sitting in the car, and they just jabbed me in the car.
That's
the only way I could get a place, and then, you know, if I had waited like a week, I probably could have gotten something right like at Walgreens nearby or whatever.
Yeah. That's somehow simultaneously the most exciting and least fun
But it was
reason
so
to go to Six Flags.
the first time I went was like, you know, it was a really long line. It was really like it was miserable, but it was also really exciting. The second time I went was like zooming in and out, so
Yeah.
it wasn't so bad. But I drove 2 people in my lab there too, so we had that.
Oh,
as
wow.
well.
Trip to Magic Mountain to
Yeah,
stick needles in us.
Exactly.
Woo!
Exactly. So cool.
All right. So I think are we ready to go? Cool. All right. So while Jeanette is collecting your models, we're going to look through them and just like see how everyone's understanding is doing so that in your final round of models, we can sit with you guys and make sure that you all have the correct explanation heading out from the workshop. But and also you might be able to incorporate some of what you learned today from our guest lecture into your models, because you might learn something new and interesting. So I am very honored to introduce our guest speaker, Professor Justin Karam. So Professor Karam was born in Pennsylvania, and after high school he went to Harvard, conducting research with Professor Jim Anderson, studying trace atmospheric radicals, and Vinny Manoharan, studying self-assembled colloidal nanostructures. And then he went on to do a PhD at the University of Chicago with Greg Engel, studying quantum coherence using multi-dimensional spectroscopies. After his PhD, he went to MIT, and after, I believe after MIT, he came here to be a professor. And so here he studies photophysics of nanomaterial and supermolecular structures and developing novel spectroscopies which can exploit the detection and the timing of individual photons. So today, he's going to share with us some of his work as it relates to this experiment. He is a great lecturer, and I always enjoy hearing him speak, so I hope you guys too. So let's all thank him for sharing his time with us today.
Well, I just want to say it's always an honor to come here. This is my 3rd time doing a lecture in this audience, and I really enjoy it a lot. And so this is intended to be, you know, pedagogical, so please interrupt me, ask me whatever questions, whatever piques your interest. And also I'm going to just talk a little bit about the things that I love about the science that I get to do here at UCLA, as well as my experience. So, can you guys hear me without the microphone, or? Oh, okay, sorry. Okay.
Do you mind repeating the question?
Yeah, no problem at all. No problem at all. So, so I'm going to tell you a little bit about our research program. Again, feel free to interrupt me. But I'm also going to talk to you in sort of big picture about one of the things we're really excited about, which is just thinking about color and what you can do by making materials that absorb and emit just beyond where the eyes can see. So, just a reminder, this is probably something you teach in your classes. Certainly, I learned it in my chemistry class or my physics class, that light is really color is about perceiving parts of the electromagnetic spectrum. So if you can imagine this, the same things that you perceive as color in the visible are also radio waves and microwaves and also X-rays and all the other things. So it just depends on both the energy of the light that you're putting in as well as its wavelength. So for radio waves can be enormous. They can be the size of buildings. The most common one that people study actually for looking at like distant galaxies is at 21 centimeters. It's a hydrogen line. So it's a line that comes from hydrogen. So they build gigantic radio telescopes out in the middle of the desert and all over the world to see that large wave. But ultraviolet and X-ray is much smaller. Those are sort of on the scale of molecules and even atoms, or even atomic nuclei as we get to gamma rays. And so our perception of color is really limited to a very small window that's right between, around 300 nanometers, that's 10 to the minus 9 meters, and about 700 nanometers. And so in that tiny window, that's kind of where our visual perception is, right about where, and you can imagine that, oops, I'm losing some of my bottom here, but you can imagine that this is just your rainbow colors, red, orange, yellow, blue, indigo, violet, sort of Vib G Roy or whatever, or Yor, Vib G Yor, if you look at it in this direction. And indigo is sort of just a made-up color because Newton was like, he thought it had to be like an even number or something, or 7. He thought it was like the music of the spheres or whatever. But in any case, the main point is that these are just these are the colors that you perceive, and there's a good reason why those are the colors you perceive. Those happen to be where the sun produces the most light. So you could imagine if you lived in, I don't know, off the star of Ceres or something like that, where it's emitting more, where the temperature is a little lower, the color will be a little bit less yellow and be emitting more in the red, and perhaps we would have evolved to actually perceive a different set of colors, maybe slightly more to the red. So that's actually where the majority of the sunlight comes from, is in the UV invisible region, and so that's why we've evolved to do that. Now, if you were an octopus and living at the bottom of the ocean, you actually might be more sensitive to red light or different colors of light. And in fact, there are ways in which that happens. But we're still in this fairly limited range in that window right there. So I'll just take a little aside. This is not my area of research, but it's something I'm fascinated by, which is the area of color perception. So just to remind you, how is color actually perceived? Well, light comes in to the back, it's focused by your lens and other parts here. It gets projected to the back of your retina. And on the back of your retina, you have a bunch of cells where inside of those cells, there's a bunch of sort of like different membrane layers. And inside of each of those membrane layers is where all of the transmembrane proteins that detect light are, okay? So essentially, you form an image on the back of your thing, then the light gets detected right over here in the back of this thing, and that forms then the neuronal impulses that ultimately you perceive as light, imaging. So we have rods and cones. We have different light receptors, right? You have your low light receptors, which are called your rods. Those are the ones, that's the black curve here. And then you have the cones, which are your high light receptors. Those are the ones that are associated with color vision. So in fact, when it's dark, your cones are not activated. So you sort of see this thing in this kind of greenish, or like people kind of view this sort of night vision grayish thing. That's only your rods that are being activated. That's also your peripheral vision is mostly your rods. So the color vision is the way you perceive color is by differential activation of these different rods. So these are where the blue rods absorb around 400 nanometers. The green rods absorb around 520. And the red rods absorb sort of out into the 600 to 700 nanometer range, which is why I say you can't really perceive light above 700 nanometers because nothing is really absorbing out there. It's not entirely true, depending on your sensitivity, your age, the older you get, the worse you are at doing this. But some people can see light, out to 800 or so. I can't, so, and I'm only, in my mid-30s, so maybe that's a problem. But it's red, yeah, it's still red. It's activating the red light parts of your eye. And in fact, it might even just be kind of this, the rods sort of extending their sensitivity, because you have so many more rods than cones that those are really, really, really super sensitive. Okay, so how do you actually perceive color? Okay, so how do you actually perceive color? This is just a fun little factoid. You have differential activation of these different rods and cones. So like, if it's mostly mostly blue, you're only activating the blue ones, and so you say that's blue. If you're activating the green ones, it's mostly the green guys, but also some red. And then every color in between is going to be, like yellow will be activating basically an equal number of green and red cones. And so for that reason, if I want to reproduce any color, I only need 3 types of pixels, right? So I only need a red, green, and blue, color perception, which is why your TVs only have 3 different pixels. They have red, green, blue. And how good they are at reproducing color just depends on how good they are at exciting individual ones of these cones. Now, like about 10% or 8% of the male population, I am colorblind and I'm specifically red-green colorblind. And that makes sense, because you see these two are really close together. That's really annoying. So if you have small mutations in your cone cells, it can make these green ones kind of overlap more. And if they overlap more, it's harder for us colorblind people to perceive the differences between those colors. Now, I have the funny story that my mom is colorblind, and if you're a biology teacher, you know colorblindness is an X-linked trait, which means that all of her male children were doomed. So it's a good example of like X-linked traits, so I always use that. So very rare in women, but very, very common in men. Now, obviously, you could also have dichromancy. So that type of colorblindness is called anomalous trichromancy. It means that you're bad at perceiving different colors. You could also have dichromancy, where you're missing one of these guys. Some people might be, there's theories out there that people might be super color people, that they have extra cones. I don't know if those have been proven scientifically, but it's kind of a cool thing that you could imagine. So my research, though, focuses on what can we do just beyond the visible, like just beyond where your eyes can perceive. And so if we kind of look, our color stops around 700, and then we have these other windows. We call them the near infrared. We sometimes call sometimes the region above 1,000 nanometers the shortwave infrared. That terminology comes from the military, because they like working in this window. That's where they can do a lot of like special types of imaging. And they like using the other acronyms MWIR and WIR for midwave, so 3 to 5 microns, and long wave, like 7 to 10 microns. I think they just like acronyms. It's kind of a famous thing. So most of things that we perceive in our day-to-day lives, the electronic transition, the transitions between electronic energy levels, are in this window here, in the visible, okay? So like this color, the color of this guy or that thing being blue or whatever, most dyes and pigments are in the visible. Almost all dyes and pigments are in the visible or the UV. So every organic molecule, every sort of thread, that's an excitation between electronic energy levels. If we go into the midwave and long wave infrared, we have our vibrations. Like that's where all of the vibrations are happening. That's where if I heat up, that's where like my body heat is producing light at that like 10 micron window. The Earth is producing energy at the 10 micron window. So if you have heat vision, you want to be out in this window. So in here, in this middle region here, it's kind of a spectroscopically quiet region. And we say that in the terms of the perspective of chemical physics, meaning this is a good place for me to do stuff if I don't want other things to interfere with what I'm doing. So there's some really good applications of this type of technology. So the first thing is optical communication. So if we're live streaming stuff, right, through our internet, if you're using Zoom for school or whatever you're doing, it's likely being carried at either 1,300 or 1,500 nanometers. That's because all of the fiber optics that they string, all the like light-based fiber optics that they string, is almost always being conducted at those 2 wavelength ranges. They're called the O and C band. Why do they do that? Well, it's because there's very few things that absorb in that window. So it's a good way to send signals over miles without them actually getting depleted. So, for example, at 1550, I can probably send a signal, 10 miles effectively, with only losing about 10% of the intensity. And so this was how we do all of our through space communications, or through fiber communications. This is so one of the challenges that we have to deal with is that silicon, which is the primary material we use for your cameras, for detection of anything. Also the primary material we use for electronics. Your iPhone has a little silicon patch on it. If you stare at it, it only absorbs to about 1,000 nanometers, and so beyond that, you can't use silicon anymore. So you need different technologies for that to actually image that technology. So you use different kinds of semiconductors for that, for example. The other thing the reason that these two bands are picked is because water, despite the fact that I said it's spectrally quiet, or there's very few things, water does have a small absorption band in that window. It's where water absorbs just a little bit, but it's enough because there's enough water vapor in the air and water everywhere that it causes some amount of losses. So you want to avoid that water band. And that's really a combination vibrational band. So it's not an electronic band, it's just like these things, the water sort of jostling around, and it has some sort of window right here. The other really cool thing is that if you look, that scatter depends on the wavelength of light that you put in. So so why is the sky blue? Well, the sky is blue because blue light is scattered more than red light, so red light comes down to you, blue light is scattered more. Blue light is higher in energy, so as you go from blue to red, you have less and less scatter. And so you in fact perceive this in this way, and so it lets you can actually image in this window with significantly less scatter. So here's a little experiment we did in our lab, just a sort of proof of concept. Here's a silicon camera. This is a webcam that you can buy them for $10. Here is a IR camera, which we did not buy, we borrowed, but it was about $15,000. Extremely expensive. This is the cheapest one you can buy. And you can do interesting things. So I just told you that water actually doesn't absorb, water does absorb in this window because of the vibrations. I'm dropping water, regular water, into D2O. That's deuterated water. So water with hydrogens that are twice the mass of there normally are. Because of that, the vibrations have changed. And because the vibrations have changed, it's actually clear in this infrared window, whereas water has some absorption, is opaque. You can actually see something cool that I would not have predicted off the top of my head, but that D2O doesn't really mix with water as well as you would think. They have actually different densities. That's for a lot of very complicated reasons. I actually don't know what the dominant factor is. I think it has to do with the way they bonding, the hydrogen bonding in D2O is. So you can see stuff in the IR that you wouldn't be able to see normally. So one of the really cool applications are like idea of making invisible dyes. So if I make a dye that does not absorb in the visible, but it absorbs in the IR and emits in the IR, I can't see it under normal cameras. So you can imagine this is useful, but I can see it under special cameras. So you can imagine people using this for things like counterfeit detection, or there's a lot of interest in the military for you want to know that the bomb that was used here was your bomb. This is really dismal but depressing, but it is an important thing. So you'll put a bunch of tracers in that are specific to your type of material. So you want to have something that you can put in that is not immediately perceptible to people, but something that you can trace later down the line. Counterfeit currency, all sorts of other applications like that. The other thing that's really cool, it's hard to see in this guy, but you can see actually through things because it doesn't scatter as much, and there's few things that naturally absorb in this window. So this is imaging through a leaf. You can see the UCLA sign right here. It's hard to see. This is imaging through a silicon wafer. You can actually see the UCLA. I have a better version of this, but I'm sorry. This is imaging through to see the Bay Bridge. I always say it's Golden Gate, but it's not if you're from the Bay Area. You would immediately yell at me, presumably, I don't know. But you could actually, this is a foggy day to visible camera, and then that same day, just a camera taking the IR, all of a sudden you can actually see in this window. So this is useful. You can imagine applications if you could make cameras that perceive in this window, applications in things like self-driving cars, like that can drive at night, or drive, well, not at night, but drive in high fog, high scattering conditions, right? Which you can imagine is probably pretty important if you're in the Bay Area or in Los Angeles this morning. I don't know if you guys saw how dead so crazy the fog was.
Wait, can I ask you a question?
Yeah, please.
So in the foggy one, we're getting that scattering. The one that you're cutting through, the light that's seeing was not scattering?
Yeah, so the scatter falls off, actually polynomial, or 1 over lambda to the 4th, if you want, for Rayleigh scatter, falls off pretty quickly in this infrared window. And so, yeah, you just get less scatter. So the main way that this is being used is rather than using cameras, because cameras are expensive. You don't want to have a camera that's $10,000 adding on to the price of your car. They're using these things called LiDAR, which is just a laser radar And so this is the one thing when I say I'm working on this, then a bunch of people ask me for hot stock tips on LiDAR companies, because it's like a fairly big investment thing. It's like the new crypto or something. I couldn't tell you anything about which LiDAR company to invest in, but I can tell you that this is a really good way to do range finding in high scattering environments. Needless to say, the other application that I view as the killer application here is basically through skin or through skull imaging. So this is a live mouse. This mouse they've shaved the head, but they haven't put a little window in or anything like that. And this is imaging at 850 to 900 nanometers. Then if you go in specific windows in the infrared, you can see all of the vasculature that underlies that mouse brain, right? And you're doing this through the skin, through the skull, into the mouse brain, because you're in this window where there are very few other perceptible sources of scatter. So this is because the tissue transmission in these windows is actually really, really high. You don't have as much absorption by other random things, and you have a lot less scatter. Those are the two main reasons. So there are a couple of reasons why I find this. Do you have a question? So yeah, okay, the great question. We're using a laser and infrared to excite, or we could use a lamp, it doesn't matter. But this is fluorescence. This is light coming out of the material, out of these guys, and that we're imaging on our camera. So that's how we have the less background. So that's actually a really important problem, because we have to find things that not only absorb, but also emit in this window. That's actually the really hard problem. Yes? Oh yeah, so in this case, something is injected. So they have to inject something in. That's another really critical challenge, is you have to have something that goes happily into biological material. So we'll talk about that in 1 second. The one thing I want to point out to you all is that I don't know if you know about how these biology experiments are done. The typical version of doing an experiment like this, where they might want to look at this, is they'll put a little window. They'll drill a hole in the skull of the mouse and put a window in it. And this is, imagine, the mouse doesn't like this very much. It's very perturbative. It's actually a hard project. Like, you have to be kind of a gifted surgeon, in a sense. So graduate students spend their entire career being really good at doing this kind of thing. And then they'll measure things like to say, oh, we didn't perturb the mice too much because they're not twitching their whiskers that much. To my mind, as an animal lover, this is a much more humane, at least that's my dream, is that it's a much more humane way to do these kinds of experiments, which could be very important for understanding like tumors and all sorts of other things. So you can do this. This is live imaging of a living mouse. You can see its heart beating. You can see other things. The nice thing is you can use traditional cameras, so you could just do what is like video rate versions of this. Now, the expensive cameras, but you can still do video rate, and you can actually do things as this thing moves around. This is a zoom in of the heart. It's cool imaging. So how do we do this cheaply? Well, I just told you that cameras are really expensive in this window, right? So your iPhone camera, does anyone know what an iPhone camera costs? Any guess? So 50 or 1,000. So you have 3 right now, or some of the new iPhones. They're about $10 each or so. Now they charge you about $1,000, but but they are incredibly cheap. They've nailed this down, and those cameras used to be like, back when I started working in a lab in like 2004, the equivalent cameras, those were like $10,000. Now they're like really dirt cheap. A crappy camera is $10,000 to $15,000. A good camera in the near infrared on this window is about $100,000. So it's still not so this is like an ongoing research question. Like, how do I drive this price down? So this is a little bit about my research, a little bit getting into my actual research questions. So we want to find things that absorb and emit in this spectral window. Like I said, there's not many things, but there are a few. So for example, there are dyes, organic chromophores, and the ones that we study tend to be these types of dyes. They're called cyanine dyes. Doesn't really matter the details. They just happen to be very good for this type of imaging. There are, the ones that were actually done for this were carbon nanotubes. I don't know if you guys learned about these, but these are like long carbon nanotubes. But from the perspective, they're really cool and they work really well. But from the perspective of like getting this into like a human imaging study, it's basically like injecting asbestos into you. So we would never be able to do that. These actually have a chance to be technically clinically approved, right? Because actually there are versions of these dyes that are already approved for imaging. Some of you guys may have even had this if you've had like certain forget what the thing is called, but like certain types of treatments, they'll inject this dye as a tracing agent. What? Oh, exactly. So you know these are, so this is common. It's not necessarily like the healthiest thing in the world for you, but it's also still like not relatively non-toxic. No, these are actually the nanotubes themselves that they're using to image. That's a good question, but because there's very few things that absorb and emit there, but nanotubes are one of those things. Yeah. So one of the things I'm going to tell you about today is semiconductor quantum dots. So I was just telling you that silicon does not absorb in this window, but there are semiconductors that do. And so the kind of ones that we look at are, the ones that actually work in this window are mercury sulfide selenide telluride, lead sulfide selenide telluride, indium arsenide, a handful of different ones that actually do absorb and emit in this window. I'm not going to pretend like we're going to use this for human imaging because, again, we're not going to inject mercury into people. They're super heavy metals, but we work with these in our lab, and we try to be very safe with them. Obviously, I'm not going to lab wearing flip-flops and, you know. So these are, now what makes these special is not that they intrinsically absorb and emit in this window, but what I can do is I can take them, make them really small, aka quantum confine them, or make them tiny, make them nanomaterials, and by doing that I can tune them so that they go from absorbing and emitting like way in the infrared into to absorbing and emitting in this window. And so that's what we do, that's our trick, is we kind of make these really small and so that they absorb and emit in this window. So let me just remind you all, and also sometimes remind myself, what a semiconductor actually is. So semiconductors are materials where they're literally elemental materials or binary materials, salts. They're actually literally salts, so you could be like cadmium telluride or whatever. That because of the way that they combine, they form a band gap. Those band gaps are like separations between their energy levels. They're filled orbitals with the filled electrons and unfilled orbitals. And they can be pure elements. So things that actually, in a pretty predictive way, like again, the periodic table is always the chemist, like it's the secret to being it's like superpower basically. Like I can look at the periodic table and be like, oh yeah, this is gonna work and whatever. But like silicon, germanium, carbon are in their pure material form are semiconductors. Carbon's pure material form you may know as diamond. Diamond's a weird kind of semiconductor. It's a really big band gap, but it is technically a semiconductor or an insulator. It is, once the band gap's big enough, you say it's an insulator, but that's the main idea. And then you could actually play games like, literally like, okay, cadmium sulfide, so this is group 2,6. Don't ask me why that's the old naming convention. It's like group 2B or whatever is this guy here. So cadmium sulfide, selenide telluride, mercury sulfide, selenide telluride. Those are 2,6. You could do 4,6, which are lead selenides. Don't ask me why, but they do actually work, and you can kind of predict, oh yeah, tin sulfide, that'll be a semiconductor, so that does actually work, surprisingly. There are exceptions, but you get the idea. So if I take a semiconductor and I quantum confine it, what I can do, if I make it really small, is I can effectively make it like what we call like a particle in a box. So like when this thing gets really small, the electron no longer can go over the whole semiconductor. The electron has to stay in this small confined region. And because of that, it opens up the band gap. It moves those band gaps so they're farther and farther apart from each other. The bigger the band gap, the bluer the wavelength of that it can absorb and re-emit light, right? So blue means higher energy, bigger band gap, et cetera, et cetera.
You mind just do that again a little?
Yeah, of course. So think of it this way. If I have a big particle, the electron can go over the whole thing, and I just feel the bulk material band gap. As I bring that system together, then all of a sudden, the energy levels between the ground state and excited state, or the band gap, get bigger and bigger. They get bigger. As they get bigger and bigger, it makes the energy levels farther apart. The farther apart they are, the higher the energy is that they absorb and emit. The higher the energy absorb and emit, the bluer the wavelength of the system. So some of these materials, like the ones I was mentioning, mercury telluride, for example, they don't even have a band gap. They're like almost a metal. They don't have a band gap when they're in the full thing. But as I make them smaller and smaller, I can tune that band gap all the way from the long wave to the mid wave to the short wave infrared. And so that's actually the trick we use. Exactly, yeah, that's right. So these are salts or whatever, so they're not intrinsically conductive. They have this band gap. And then like gold, which has half-filled orbitals so that it has any number of states that it can go into. But, so you have a different, they're the confinements in the plasmon. Anyways, it is related but different, you know. So once again, in my group, we've been really interested in these mercury chalcogenide materials for all of the reasons that I just discussed. And we actually take these guys from having, well, they actually say negative band gap. It's a weird terminology, but it means it's a metal. And they can quantum confine them all the way through the visible. And we can make other materials. So we do this through chemistry, through wet solution phase chemistry. So I mentioned before that, you know, there's different ways to make nanomaterials. Well, I didn't mention it, but I'm sure you guys have talked about it. But the way that we're doing it is literally probably very similar to the lab you just did. We take salts, we stick them into a thing. In this case, this is a high temperature synthesis, so you have to heat it up in a long chain alkane. So like you take it in octyl decylamine, so it's like this really long chain alkene, or octyl decyl, whatever it is. Yeah. Sorry, I don't do the chemistry. My students do it, so I don't have to worry about it. So we heat it up to a very high temperature, and it takes the salts and it forms these tiny nanocrystals, which we can control the size using temperature control, using the precursors, using all sorts of other chemical tricks. And then this reaction, depending on how long we wait or our particular sets of controls, we can make like very small materials that are all roughly the same size. This is a great, actually kind of a cool example of like actual basic chemistry leading to real applications. So my postdoc advisor developed this method in like 1990 and refined it, and now you can walk into every Costco and buy a quantum dot television where they now can make every single quantum dot is exactly the same size to within one atom based on the wet chemical method, which is extraordinary. I mean, that's precise control that you wouldn't be able to do like with an electron beam lithography method or anything like that. So it took, 25 years for that to happen, but in the intervening 25 years, we saw something really amazing happen and become a very commercial technology. In my group, we do something a little bit different. We actually study these things called nanoplatelets. So nanoplatelets are, instead of being a quantum dot or a spherical particle, it's a 2D sheet. And these 2D sheets have only like 4 atoms. They're only like 4 to 6 atoms thick, but they're really, really large. And so that gives me the quantum confinement along one dimension, but along the other dimension, I can like absorb all of the light that comes into the system. And so it's a fun playground for looking at different properties, extreme confinement. So instead of having confinement in all 3 dimensions, I now have really 4 atoms thick. And we can actually make these guys just by controlling the temperature and some of the conditions of the reaction. So actually, you have that type of control. In addition to making spherical nanoparticles, you can make rods and sheets and all sorts of other stuff, which was, some of it was incidentally discovered, some of it was by design, but that's kind of the idea. We can actually make, in our case, we're making cadmium telluride nanoplatelets, which we then can add in mercury salts, and those will actually replace the mercury cadmium 2+ will be replaced by the mercury 2+ because of salt reasons. I don't remember. No, I mean, there's like theories of hard salt, soft salts. I couldn't actually explain them to you, but maybe you guys know them. And then one of the things we do is we can then tune this further so that it absorbs and emits in the infrared by actually creating traps in the system. So what we'll do is we will kind of roughly treat these nanoplatelets, and then they form little like clusters on their surface, and those things actually can then emit light. So that's something we've been doing to make tunable nanomaterials. How much time do I have? Am I good?
Maybe like a couple more minutes.
Okay, great. So I'll just wrap up. Let's see.
What's the application?
Right, good question. So there are a bunch of different things we're interested in doing with these types of materials. So this is a good slide for that. So one area that we're really interested in is the ability, since I can tune the size, I can do different colors. And so let's say I want to tag a bunch of different things in a living system, like, the inside of the cell, the outside of the cell, the mitochondria, the whatever. So I can now, instead of just doing that in the visible, I can do that all through the infrared and then image that deep into tissue. Another advantage is the ability to do this in a cheap and scalable way. So I can make molar, that's the magic trick of chemists, is we can make molar quantities of identical things. The mole is 10 to the 22 versions of that. That's amazing. You can't make 10 to the 22 computer chips, but you can make 10 to the 22 of atoms very easily. So we could do this, and we want to do this scalable. So this is a synthesis that we used to do, where you actually make such a large amount at a time that the way you can do this is by injecting really fast. So you have to use like an air gun to shoot the precursors right in, so all the reactions start at exactly the same time. This is called fast injection. But it's probably the only synthesis you use a gun for, which is a joke that kills in other places. But you can then use these guys to make solution processable electronics. So then I can use these guys not just as emitters, but then to drop cast them onto a surface, just like they make a silicon iPhone, but now I'm drop casting this guy, and it's taking the light and producing electrons that I can use for other things. There's some other cool applications where you could take these, have them absorb infrared light twice, and then convert that into one visible photon. So I could use that to detect stuff in my camera or in a normal cheap camera. That's called upconversion. That's a really cool process. And then, so like, one of the things that I just find really exciting is maybe we could take these really cheap materials, drop cast them on a surface, either doing these upconversion or just directly detecting it, and we can actually detect infrared on a very cheap platform. So I can actually detect this light just, instead of buying a $100,000 camera, I can make something really cheap. And then it could be omnipresent, and the application space may be way beyond what we can see. So for example, could we see, people have noticed that bad apples will have infrared splotches on them. That would be something you could see. They've looked at this for quick detection of cirrhosis. Like you can see this some things in cirrhotic livers, all sorts of other things. So this is just ideas out there, but yeah. Thank you.
Very cool. Thank you. All right. I think at this point, we're all going to go and grab our lunches and eat outside. So it's 12:15 right now, so just so we can keep on schedule, I'm going to ask the grad students starting around like 12:35, 12:40-ish, to start going around to where the teachers are sitting outside and start doing your final draft of the model with them. So just checking, seeing how things are going, making sure that the understanding is good and everything. If anyone has any last questions for Professor Cram, I'm sure he's
I'll move around to lunch.
Yeah, he's grabbing lunch too, so I'm sure he'll be happy to answer them as we're all heading out. And then at around I think 12. What time should we be back here, Jeanette, for doing the? 12:45. Okay. Okay. Yeah. So we'll all head out now, and yeah, grad students around maybe 12:35. Let's start going and checking in with teachers and doing the last model. So everyone should have a little card that has whatever your sandwich was, and then we'll get organized outside. And then if anyone wants to wash their hands before lunch, the restrooms are down that way, or you can use hand sanitizer.
Good gear.
Thank you.
Yeah, it'd probably be good.
Okay, so I'm going to go ahead and get us started because we don't have a whole lot of time. So thank you for like that last 10 minutes. I don't know about you all, but the conversations we were having, grad students in particular, thank you. I feel like those last 5 to 10 minutes, I don't know if it's because we were fed, we were outside, but like, it was like, whoa, I heard so many people saying, oh, okay, so size this and that, and it was like making connections that we hadn't made. So thank you, grad students, for being there for us during lunch. One more time, thank you. That was awesome. So we're gonna shift into really like practical classroom application stuff. So we're gonna do a couple of things. One is my passion project, science identity, and then we're gonna talk a little bit about specifics of where this might fit in your curriculum. So it turns out that, as you know, I'm all about the brain and learning, and there are factors that affect our learning that sometimes we're not aware of. And one of them is something called science or STEM identity. And we all have identities. We have gender identities, racial identities. We might have identity as a person, as an individual. I identify as a mom, as a sibling, as a daughter. So we have all sorts of identities, and those identities we bring with us to the classroom. And so sometimes those those identities, there's a misconnect or a disconnect with the classroom experience. And so with science identity, it's something that we want to support for our students. So there are so many definitions of science identity, but a simple definition is seeing ourselves as scientists, which incorporates what we do as a scientist, how we are seen as a scientist by others, and how we perceive ourselves and our competence within science. So I've put in a couple of like just my, again, things I'm passionate about. Some interventions have been done to try to support diverse students in STEM, and they really focus on science identity. And when you focus on developing this identity, particularly for marginalized students, what it does is it actually gives them more engagement in the classroom, makes them feel more like a scientist, more like this is something that's potentially a future career for them. And it increases their grades up to a year after the intervention, if not longer. I mean, the study that I put in here tracked grades a year later, but you can track it even longer after that. And as high school teachers, even though we don't necessarily teach psychology, right? We're teaching biology, chemistry, physics, integrated science. We might be teaching anatomy, physiology. Science identity is something you can support through the nanoscience labs that we do here. So one cannot pull off being a particular kind of person or enacting a particular identity unless one makes visible to others one's competence in relevant practices, and in response, others recognize one's performance as credible. So I took that quotation because I really like it, and it ties into that little graphic up at the top. But I'd like you to just take a moment and think yourself, how did you develop your identity as a scientist or as a science teacher? So what was it that sparked your identity as a scientist? Because we all went into science, right? We're all science teachers. So there must have been something that got us along this track. We didn't choose a different career, we chose this career. What influenced us? And it could have been your elementary science experiences, could be something that you experienced in college, could even be something you experienced later in life. Many of us might be career changers into teaching. So think back to what developed you as a scientist, and just jot a few ideas down right here. Okay, now that's a pretty personal question. So when I ask questions like that, in order for me to feel comfortable enabling my students to share out, I have to know that they've established a safe space. I'm not sure if you feel that way, so I'm not going to force you to share that out. If you would like to, you certainly can as a team. Instead, go ahead and flip to the back. This is a bit more safe, so I do want you to share out here, but I'm not saying you can't share out about identities on the front page. I am not requiring an identity share out. I would encourage it if you feel safe within your group to share, see if there's any commonalities. Instead, I want you to think through, how does this lab support your students' development of identity? In what ways do they grow as their performance as a scientist? In what ways do they start to recognize as themselves as a scientist? In what ways might they grow their competence as a scientist? So think through those three things, the three aspects of science identity, and tell me what you think. So this part is a group part. Please talk it through. Feel free to jot it down. This is where I really want you focusing on teacher moves, right? So this is like, oh, you know, I'm gonna make sure that my students do this, this, or this. So our teacher hats are definitely on at this point. So please feel free to like talk as a teacher right now. I'm gonna give you about 5 minutes to do this. And again, if you feel comfortable, please feel free to share about your identity. I'm not forcing identity sharing though if you don't want to. Okay, go ahead. 5 minutes.
This in nanoscience experiments is that the student have the tools, you know, and they can conduct an experiment like a scientist. And this is scientist, but that's what they're saying. How does this lab support your student development of scientific thinking?
Okay, I'm gonna have you do 1 more minute. Okay, so I'm gonna call you back. So again, thank you for thinking through identity and how we can develop that identity. I might encourage you to consider really emphasizing to students that this is cutting edge technology, that it's a long lab, it's a difficult lab, right? This is certainly a multi-step, multi-day process, but look what they were able to accomplish. And it's that like positive feedback that it really is, that's gonna emphasize the idea of competence, right? That like, you did this, like you were able to get there, and oh, you made a mistake the first day, but you fixed it and you figured it out in the end, right? Like look at all the steps you got through along the way. I think really like narrowing in on performance recognition and competence can be particularly helpful. And then taking the work from like the quantum dot lecture and bringing in what's actually going on, what's out there in the world, because then you're really recognizing, well, if I can do this, then in 10 years I can do that, right? That even the scientists who are currently doing it, they started by doing the same labs that you're doing right now. This one in particular, this could be placed in so many places. And students could do it if they were in physics, in chemistry. We are gonna do the last activity, and then you're gonna get to go home. So the curriculum integration, I'd like you to talk about this whole page with your team. And this will be our last page. You wanna think about where could this fit in your curriculum, right? Is it in an NGSS class? Do you teach an elective class that you could fit this in somewhere? What kind of demo could you use? Would you use the same coffee demo? Would you use something different? I will say, I heard in that final discussion, I started to hear a lot of discussion on scale. So just a quick reminder that when you do these mental frameworks, use those cross-cutting concepts, because the cross-cutting concepts really help to identify themes that you're gonna talk about lab after lab after lab. And then last one is that classroom strategies, things that you could use to really help support your students. The nice thing would be if you bring in identity into this one, that would be awesome, but just thinking through all of these, and then this is your last task. Yeah? Is this one for the three of us? No, one for individual. Do you all have one?
It's usually one per table.
Oh, one per table, sorry. I always forget, sorry, my bad. One per table. Thanks. Yeah. Okay, so final wrap up, capture that one. Go ahead, 5 minutes. Oh, we do, yeah. Okay, so we're gonna actually break you up into, we'll do chemistry, life science. I don't know if I heard any physics. He's okay, so chemistry will go there. Let's do middle school, and then integrated science, I think, there too, because I don't think we had that many middle school. Chem, life sciences, integrated / middle school. Perfect. I think it's mostly chemistry, if I remember. Middle school's over there. No, middle school's over there, chemistry's over here. I know. To get signs.
Yeah, next time we should just put placards. Probably easier.
another conference right now. Talking about who is the computer science and chemistry teacher? Okay, so today is the Computer Science and Science Summit for the California Association of Science Educators. So I'm going to go give a presentation about computer science and chemistry. So feel free next time you come to ask me about comp sci because I love doing coding activities in my chemistry class too. So.
And we're teaching a computational nanoscience workshop later on, which you guys should attend because it's going to be awesome. And that one is virtual,
Virtual, so yeah, you can like come in your jammies.
November, yeah, it's one of the November ones. That sounds right.
Yeah.
November 12th, maybe, yeah.
Yeah,
But that one's a virtual one, so.
Definitely come because yes, computational thinking is something that I think it's one of those SECs I think some of us struggle with understanding. So
Yeah.
yes, awesome. Okay, so nice to meet all of you. I hope to see you again.
Thank you, Jeanette.
No, thank you. Was this one up? Oh
Yeah.
yeah.
So, yeah, you guys can go ahead and keep working maybe for another like 5 or so minutes. And then just before you all leave, I just have a couple of wrapping up announcements before we send everyone on your way. But please continue to chat amongst yourselves.